Thank you very much. So first of all, thanks to Denjo and all School of Theoretical Physics for putting this wonderful event together and for invitation and for opportunity to tell you something. It was a wonderful week. I definitely did learn a lot, as probably all of us did. I even did learn something while preparing my talk. I will get back to that. But I realized that maybe unconsciously I picked a topic that's full of research that has been done either at DIAS or by people affiliated to DIAS. So I want to also take this as my humble appreciation of the impact this institute had over the 85 years on the field that I'm working in. Also, this is probably my 5th or 6th time in Dublin, and it always was very nice the first 7 days I came, and then the 8th day, it started to be regular Dublin weather again. So my talk is going to be a little technical, and I'm going to try to tell you way more than I can fit in 1 hour. So this is my take-home message for you. And if you remember only the next slide from my presentation, I think I'm going to be happy. So I'm not going to talk about physics of the brains in the context of the name of the workshop. I'm more going to talk about physics on the matrix spaces, what's happening on the brain. And then this physics is described by random matrix ensembles and some calculations within those ensembles. The particular ensembles that I'm going to talk about are usually rather challenging, but there's a lot that one can do anyway using various techniques. And the main technical point I would like you to take home is that even though the probability distributions in these ensembles are going to be symmetric, the ground states, i.e. the solutions of the saddle point equations, which have the smallest free energy, which are the most probable, can be asymmetric. And that's spontaneous symmetry breaking we all know and love from particle physics. And one more thing, anytime somebody says good, bad, and ugly, they usually mean the ugly. So I don't think this audience, either here or online, does need too much of a motivation. I think we all have shown at certain point in our lives this kind of slides where we emphasize that when we unify things in physics, wonderful things happen, and we are waiting for the final unification that's around the corner for 100 years already. And or more technical level, we probably all also have shown slide like this, where we say that when we quantize gravity, no matter how we try to approach it, sooner or later, a notion of quantized spacetimes pop up. That simply, if you try to ask two energetic questions, the spacetime will just refuse to give you answers under certain length scale. And in the context of this workshop, the last point, the emergent spacetimes in fundamental formulations of physics seem to be the smoking gun that something is happening there. And fuzzy spaces are a very nice and very tractable example of spaces with such structure. So the bottom line is that when you construct the fuzzy space, you take your round manifold or smooth manifold and you separate it into Planck-like cells. However, this picture is misleading because the boundaries between the cells are not sharp. You cannot separate points under certain length scale. You cannot say here or here. So the boundaries are truly blurred, or we say fuzzy. And I like to show this image. Yeah, here it is. Yeah, this is a standard optical illusion where if you look somewhere, the snakes whirl around somewhere else. And when you follow the movement of the snakes always stop moving and move somewhere else. And on fuzzy spaces, something similar happens, but completely the other way around. That if you do not look closely, the space looks regular, but when you try to look more and more closely, the space starts to be blurred and starts to do things. So the way I like to think about it is that at the boundaries of the cells that I have shown you before, if you try to pinpoint the boundary, things like this start to happen, and the space refuses to give up. It refuses to give you information under certain length scale. And Yeah, we already seen also in some talks. Even yesterday, it was mentioned that the fuzzy spaces appear in things like condensed metaphysics, and we all seen it here and there. And again, in the context of this workshop, the most important part is the total fuzzy spaces as solutions to the matrix models, and Harold has a recent nice book about this. And on a more technical level, as Jens mentioned, for quantile time, we now have known how to formulate these things from two different perspectives. That's something that Samuel has mentioned by the MP3 file in the first day of this talk. Yeah, it was a long time ago, wasn't it? That you can either formulate the fuzzy space by cutting off the algebra of functions and therefore losing precision in pinpointing the points. But then these objects are not closed under multiplication, and you need to, you need to recall some group theory dark magic to make it closed, and the price you pay is non-commutative product. Or you can start with matrices and realize that certain representation of SU2 gives you finite dimensional representations of SU2 give you space where you can realize your fuzzy sphere. And here the fuzziness, the blurriness of the space is essentially the Heisenberg uncertainty principle. And in one way or another, you can do the same thing also with the plane. I'll talk about that a little later. So now we do physics on these spaces. So in the context of this workshop, well, for me, these matrices that define the fuzzy space somehow are result of the matrix model dynamics. Yeah, you either do the numerical calculation, or in one way or another, you obtain a solution to the matrix model. You obtain your emergent space-time as a membrane that's a solution of the matrix model, and then so these are the matrix, the coordinate functions, the matrix coordinate matrices, and then you try to see what kind of physics you can do on that space. And we probably are far enough, all of us are far enough in our physics career that we are rather deformed, than the first physics that comes to your mind is scalar field theory. So you can take Euclidean scalar field theory, the commutative version, then take the dictionary that you find in the textbooks and translate this theory into a non-commutative version. And then there are plenty of fine books that review what happens when you try to ask field theoretical questions in this language. And for my talk, what's important to know that this path integral now is a matrix integral. It's a well-defined finite dimensional matrix integral. You can try doing large n limits, but at given n, this is a well-defined path integral, and it's a matrix integral. Yeah, it's answering questions in fuzzy field theory is computing expectation values in some particular random matrix model. So let me tell you something about random matrices. Now, again, details are not too important because not only you know the details, some of you have contributed to these details. So the idea is that when you have probability distribution in the Hermitian matrix model that is invariant under the conjugation by SUN, you can diagonalize, and if you ask invariant questions, then the angular degrees of freedom don't contribute, they integrate out for the standard nice matrix models. And there's the Vandermonde determinant, the repulsion in between the eigenvalues. So you obtain an eigenvalue model that's a little different, but still the angular variables have dropped out. And now you do some n analysis to figure out how large your contributions to the action needs to be. And what you find out is that for things to be well defined and all the terms to play a role, there needs to be an n squared factor in front of the action. So if you take large and limit, then this probability distribution localizes on the minima of this expression. So you look for the minima, and then you find out that the saddle point equation is essentially an equation of mechanical stability of n particles in potential V with some kind of repulsion. And this is a very important and very, very instructive insight and the way of thinking about that. So the intuition in the simplest case is that when you have positive R in this potential, and G is always positive to have things bounded, then without the repulsion, all the particles would like to be down in this minimum, but with the repulsion, the particles spread out, and this green line denotes the probability distribution of finding a particular eigenvalue. Yeah, this is the eigenvalue distribution in this matrix model. And when you have R negative, sorry, they should be negative, then the eigenvalues start to spread apart quite far. And at certain point where this maximum is too high and the values are too deep, your eigenvalue distribution simply separates. The eigenvalues separate, and there's a phase transition, and you obtain a two-cut solution to your matrix model. And the cuts become more and more separated for negative R. However, when R is even more negative, when the valley is deep enough, and it can confine the eigenvalues even though they repel each other, there is also an asymmetric one-cut solution to that saddle point equation. However, we can quite straightforwardly see that the energy of this distribution is much larger than the energy of the blue distribution, because here the eigenvalues are higher in the potential and they're closer to each other. So both the energy contributions are greater, and this solution is what I will call not realized. It's not dominant. The dominant is the blue solution, because it has the blue solution has lower free energy, i.e., in the sense of the matrix ensemble, it's more probable. And if you do the large and limit, only the most probable solution will contribute to the path integral, and the fluctuations around that most probable solution will contribute to the expectation values. Okay, so now first a couple of matrix models that I'm going to mention are related to fuzzy field theory. So we have already seen that. This is the full model, the full probability distribution of the scalar field theory around the matrix ensemble. And as you have noticed, I'm putting numbers here to the ensembles that are going to appear. My talk is named the matrix ensembles from fuzzy field theory. So this is ensemble number 1. So this is true full-fledged fuzzy field theory on fuzzy sphere matrix model, where there are commutators with the what essentially are the generators of SU2. Now, this is the sentence that Harold Steinacker said all the way in 2019 in the Corfu conference. I really like it because that's how it is. When you have a matrix model, the first thing that should come to your mind is try putting it on a computer. So there have been people already more than 20 years ago that have tried to say something about this model using numerical Monte Carlo simulations. And what they found was that strangely enough, what happens is that the asymmetric one-cut case in certain region of the parameter space, yeah, sometimes I have m squared and sometimes I have r. I'm sorry about that. I believe that this audience can figure these things out quite easily. That in certain part of parameter space, the asymmetric solution that I mentioned, that without the kinetic term was suppressed, now becomes the dominant solution. That simply the the kinetic term introduces some kind of attractive interaction in between the eigenvalues, such that they don't mind being packed that tightly together. And here, the asymmetric one-cut solution is the dominant solution and has the lowest free energy. So this was a result of a lot of work, yes, starting in 2014, and then you can see a lot of familiar names popping up in this list, and Marco Panero has written a nice review in the conference proceedings of the Corfu conference. And now this has a meaning on the field theoretical side, that this phase diagram, and but on the field theoretical side, not this region is interesting. This region here is interesting. That corresponds to the symmetric two-cut solution of the matrix model. This is an image of where these people have found it numerically. It's called, in the field theory context, it's called the striped phase, and it's a phase that breaks translational invariance of the space. That the field doesn't oscillate in the broken phase, it doesn't oscillate around one or the other minimum of the potential. It oscillates around both minima, different minima in different regions of the space. So this breaks spontaneously the translation symmetry. And if you heard about it, you probably know that it's related to the fact that the space is non-local. This couldn't happen in local theory. The fact that the theory is non-local due to the fuzziness of space is crucial here. And yeah, this in regular field theory, this doesn't happen. This is the phase diagram or usual fuzzy field of usual field theory on regular continuous space, where we have the usual unbroken phase and the broken phase, and this is essentially 1D Higgs mechanism. So, and on the field theory side, this is related to UVR mixing that Harold Schweinmacher mentioned in his very first talk of this meeting. And conceptually, UVR mixing is due to the fact that very high energetic quantum fluctuations can have consequences at large distances. When you try to confine the fluctuation in one direction, at certain point, you just cannot do anymore, and the fluctuation just spreads out in the other direction. So UV physics in this direction can influence things happening far away in this direction. And on technical level, it's due to the fact that when you do planar contraction and non-planar contraction in this diagram, you obtain two things that are different. And they are different even in the larger limits. This is technical stuff. I don't want to go through that. This sentence is important, that when you do large n limit of your fuzzy space, the space becomes continuous, but the theory that you defined on it remembers its fuzzy origin. Yeah, and Harold nicely explained that using the string states last week, that simply no matter how large your n is, the quantum fluctuations that run through the non-planar loops simply do still carry the non-commutative information and destroy your theory, even though you cannot see it on your external legs. Now, and the same thing happens also in theory on the plane. And in principle, there would be a way how to take care of this at one loop, but if you started to put diagrams like this on legs in your higher loop diagrams, then everything would fall apart and the theory is not. Okay, so far we have seen one matrix ensemble, and we have seen that that ensemble says that that in the phase diagram of that ensemble that there's two-cut symmetric phase that corresponds to some UVR mixing things on the field theory side, and there's asymmetric one-cut case that is very strange when you look at it as matrix ensemble. And let's try now to more carefully discuss the asymmetric one-cut case in the matrix ensemble. Why is it strange? Because the probability distribution was, let me stress that, Yeah, the probability distribution in that model is symmetric. When you switch signs of your eigenvalues, the probability distribution, the probability of that particular configuration is the same. The probability distribution is symmetric. However, the lowest energy state is asymmetric, and the symmetry of that probability distribution is broken spontaneously. So now what you can do, that this is the kinetic term of the field theory, and it breaks the conjugation invariance of the probability distribution. So the EU integral that was there before for free, now it is non-trivial, and yeah, you can define some kind of effective action as this integration of the kinetic term. And there have been attempts how to treat this perturbatively and calculate this effective action as a perturbative series in powers of the kinetic term. And yeah, you lose a lot of rather complicated field theory there. But what you end up with is a multi-trace matrix model. Multi-trace is the word of today. That opposing the single traces of your matrix, like C2 here, yeah, this is the trace of M squared, you get powers of the traces. Here, for example, we have trace M and the whole thing squared. So this is something that's referred to multi-trace matrix models, and it's also been quite known, especially it appeared in the string theory context. So you can turn your multi-trace matrix model into a single trace matrix model simply when you take the variation of this action, you obtain a saddle point equation that looks a lot like the equation we had before for single trace action. However, the coefficients that appear in the effective potential are dependent on the moments of the solution themselves. And in the large N limit, you can solve this by self-consistency. That you solve this as a single trace model, then you compute the moments of that solution, and then you realize, aha, but the potential depended on my moments to begin with. So the solution for your moment is not truly an expression for moment, but a self-consistency condition for the given moment. So the equations are more complicated because for some moments, some of the moments are not given by the procedure, but solution for are free parameters to be computed. But in principle, it can be done. So you can try analyzing this as a rather complicated matrix model. It can be done either by Monte Carlo simulations or by some other approaches. The bottom line is that this doesn't work. That this matrix model simply has bad properties. It doesn't describe the field theory as you would like to. And the point is that simply the interaction is either too large, is way too large. It's either too attractive or too repulsive because you have cut off some expression. You have basically cut off some asymptotic series at finite order, and then you have pushed that order way beyond what is capable. So there is so this was model number 3. Model number 4 now is something that I call non-perturbative approximation, and what it does is due to some ideas already made quite some time ago. What it essentially does is that it figures out how to compute the full expansion of the first line, and then discards the rest. When you look at this expression here, that's exactly that. Here we have a function that completes the asymptotic series of the first line in that perturbative expression, and there is some reminder that vanishes when you compute it for moments of semicircle distribution. So essentially, if we drop this reminder term, and we consider only model like this, we are making approximation of eigenvalue distributions that are not too far away from semicircle. We will see that this approximation works much better than it should, and to be honest, I don't completely understand why. It just works rather well. So this is the another matrix ensemble. It's a multi-trace model, but with some rather complicated function of moments in here. But it takes into account it needs only the first and the second moments. It's multi-trace only in the first moment and in the second moment. And now, as you can see, with my student Maria, we spent quite some time trying to figure out how to handle this. And there was a lot of work, technical work that I don't want to go into. However, at the end of the day, you obtain a phase diagram like this. There's a lot of Pade approximating and things like that. But you can do it, and you can obtain a phase diagram like this, where here you can show that the asymmetric one-cut solution is the preferred solution, that it does have lower free energy than the two-cut solution that normally would be preferred in the pure potential model. And we have also identified a triple point where all the three phases meet. And when you compare this, the diagram that I have shown before, it does recover a lot of those features. Yeah, there's the stable asymmetric one-cut case, and there's a triple point that's located roughly where the numerical people have found. Not completely, but qualitatively it is there. But the main difference is that our transition line here asymptotes the vertical line, whereas the numerical calculations show that this line is a straight line, goes all the way. So to fix these issues, the location of the triple point and this asymptotic behavior of the transition line, what you can do is you can take lesson from here, and you can try to guess the behavior of the remainder terms along these lines. Yeah, you can try.
So what is F with C comma? It's only one action, right?
Yeah. What I'm trying to say is that you can take. This is a different function F.
Oh,
this is a super bad copy paste fail of copying things from two different places where that's the thing. I'm very sorry. Maybe the square bracket opposing to the round bracket can tell you something. This is a different. You take a general function of these combinations of moments, and you try to use something like that. And what we have been able to show was that no matter what you do, you're bound to fail. Nothing like this that doesn't spoil the nice properties of your phase diagram is going to fix the bad properties of your phase diagram. So the bottom line is that you need to go non-perturbative to explain those things. That if you try just to compute the effective action using moments and some kind of perturbative approximation and then non-perturbative completions of your perturbative approximation, you're bound to fail, and this is as good as you can do. There's nothing better you can do using these kinds of techniques, and you need to work on something completely different. Okay. There are different matrix models now. So now I'm going to switch gears a little. As I mentioned, the striped phase is related to the UVR mixing, and then there are two theories that fix this problem, that remove the UVR mixing from the phase diagram of the theory. So what you can do is try to analyze the phase diagram of the theory using our techniques and see whether or not the striped phase disappears. Because the striped phase is a result of the UVR mixing. So if you have theory without UVR mixing, then the striped phase shouldn't be there. Now, you notice I have a matrix ensemble without a number here. And the reason is that when I was preparing these slides, I realized, as far as I know, Nobody has tried putting this matrix ensemble on computer. It begs to be put on computer, and nobody has done it. And I realized that 2 days ago. Maybe Denja knows about some reference, but I don't know. It's technically rather complicated, but at the end of the day, these are just numbers. For computers, numbers are, any number is good as a different number. So I think it would be very interesting to analyze this model numerically and see whether or not the striped face truly disappears from the phase diagram. However, what we tried was doing the non-perturbative approximation, the second moment approximation that I have mentioned for this kind of model. And what we have been able to show that the striped face doesn't completely disappear because we don't analyze the full model. We only analyze approximations of the model, but we see that the region where the striped face exists does recede. That as we turn on parameters that slowly turn on the Q term in that action, the region where the two-cut solution was the preferred one does recede toward the right. So this we claim is a hint that that model with that Q truly does what it claims to be doing, and the striped face is going away, and the UVR mixing is big. On a different front, you've probably all heard about work of Harald and Reimar which is probably much less recent than we all would like it to be, where they have managed to formulate models that remove the UVR mixing on the plane. Now, this is a very different kind of removal from ideological point of view, but from technical point of view, it's again some kind of modification of the quadratic term of the field theory. Now, this can be described by truncating the Heisenberg algebra. So you take the creation annihilation operator essentially, and these two infinite matrices do generate the non-commutative plane, and when you cut this off the finite dimension, you obtain some kind of approximation that in the large n limit becomes the non-commutative plane, and you can show that in that case you can show that the extra harmonic potential introduced to fix the UVR problem turns into this kind of trace of m squared with a fixed external matrix that's just a diagonal matrix of increasing numbers. So here is your matrix model. Yeah, you have the kinetic term coming from the commutators with the coordinate matrices. You have your extra term that is there that supposedly fixes the UVR mixing, and you have the potential. Again, I have switched notation for the parameters in the potential, again, just to keep you focused. And this model has been analyzed numerically by my colleagues in Belgrade, and they did find a shift that is consistent with the removal of the UVR mixing. Now, Dragan has a different story about renormalizability that I believe is just the rephrasing of what I'm saying here, but the bottom line is that numerically, this model seems to be doing what it claims to do. Can we see that analytically? Well, first of all, let me mention that you can calculate the effective action of this kinetic term without the curvature term by the same techniques, and this was done by my student as his master's project, and the structure there is the same as for the fuzzy sphere. Essentially, the numbers are different, but the effective action is the same, which tells you, which is to be expected, is a non-commutative space, some kind of effective action for the kinetic term. It has the same structure, just with the different numbers that reflect that we are dealing with a different term. And therefore, the phase structure of this, using the same procedure for this kinetic term is not going to give us qualitatively different result. So let's concentrate on the curvature term. Yeah, this is actually much more simple technically than the thing we have seen before, because yeah, this is just matrix integral with fixed external matrix, which in principle is rather simple. Yeah, this is simple. This is Harshchandra-Atkinson super integral, but and it's given by some determinants of the eigenvalues. But if you want to actually calculate some probability distributions, it's better, and it's the only thing you can work with is the perturbative expansion. This is the thing that we currently have to the 6th order in GR, and that's the thing we are currently working with. And you can calculate the phase structure of this rather complicated matrix model, but it's a multi-trace matrix model, which now, however, has some rather obscene powers of the eigenvalues here. Yeah, it introduces a 12th order term into the effective potential. So you just need to run your computer and let it do what computers are good at, computing. And this is a phase diagram that we have obtained. And I'm going to show you this result because this is more recent. So this is our quartic coupling, and this is up the negative mass. And the region of symmetric one-cut phase compared to the region of symmetric two-cut phase has shifted upwards in this model. That means that the symmetric two-cut region again recedes, but it recedes in the different direction. Yeah, remember before it receded to the left. Now it recedes upwards. So the mechanism of removal of UVR mixing seems to be different, but it still is there. And we have also identified asymmetric solution in this model, but since the model is symmetric, it's always subdominant. It's never is preferred. However, if you have, in the beginning, I have told you that if you remember just this one slide, I will be happy, and that it's still true. But if you have capacity for 2 more pieces of information, I'm going now to give you one new piece of information that's extremely like result of the work that we're doing currently, and this is something we've been struggling with in the last couple of weeks. And what we are seeing in numerical simulation of the full model, yeah, this is the full matrix model. Where is it? Where is it? Here. No, not this one. Sorry, this one here. We're not taking the perturbative expansion. We are just analyzing this full model numerically using Monte Carlo. And what we see for certain small values of quartic coupling is some kind of different phase, a new phase. I believe this is 40, 20 or 40. Yeah. This you know, it changes, so I don't really remember whether this was 20 or 40, but it's at that order. You can see that in certain part of parameter space, the eigenvalues start to condense around 0. Yep. That there's a peak around 0 that's prominent, and in principle it shouldn't be there. So we conjecture that this is a different phase of the model. It's not symmetric or asymmetric one-cut or two-cut. And what we actually think that this is a 3-cut solution of the quartic matrix model, that somehow the effective action, the interaction with the external matrix can make a solution where the eigenvalues are located here, here, and here stable. Yeah, remember, these are basically particles that repel each other by van der Monde repulsion. So you can imagine there's a solution where the eigenvalues are balanced on top of this peak, but that solution is mechanically unstable. Yeah, if you shake this a little, these eigenvalues will drop to those minimum. So what we think is that is happening is that the interaction with the external matrices somehow stabilizes this kind of three-cut solution. Or perhaps, yeah, as I mentioned, there are some funny terms that resemble higher order in the potential. So maybe this what this means is that the effective potential for this model is not quartic, but it's of some higher order and therefore has more than two-cut solutions. So this is something that we are currently trying to see. Yeah, this is a better image that Dragan has sent me last night, and I just wanted to include it to appreciate his hard work that he's been doing for me to include a very fresh image in my presentation. So essentially, what we claim is that here there's a small region of parameter space for small quartic coupling and some values of the negative mass where we see some new things happening. And I know that Denjo and Samuel have seen strange things happening also on the fuzzy sphere around the triple point and some strange solutions and things like that. So those ensembles seem to be less innocent than they claim to be. Okay, now you can go beyond phase structure in field theory. You can try to calculate correlation functions, and there are some numerical hints that correlation functions behave very differently than in the classical continuous theory. Jens has a question.
Before you started, I have a question. When you take the you talked about the phi to the fourth theory, sure, non-commutative. When you take the matrix model, either from Mills or from membranes, the commutator square, and then you take the n going to infinity limit, you either get the classical membranes of some topology, but you can also get star product models where you take where it's not the Poisson bracket of function squared, but the star product.
Okay.
And the question is, do you know anyone who has numerical work or any kind of work on these star product models with commutators? I once noticed something some truncation, actually quite early in 1990, which had a Lux pair, but that's the only thing I know. So the question is, do people have considered star commutators? I mean,
not
phi 1 star phi 2 minus phi star phi 1 in bracket square.
I'm not aware of anything like this, but clearly that doesn't mean it doesn't exist. I'm not aware of any kind of this work. Sure. So, but then there are things that you can compute beyond phase structure that hint that a lot of different that fuzzy field theories are very different than commutative field theories beyond the phase structure. Yeah, there are some different critical coefficients in correlation functions. There's a different behavior of entanglement entropy because in normal at the scales where the fuzzy field theory becomes non-local, your area law for entanglement entropy becomes volume law, and people have been able to see this numerically. And now it would be interesting to construct matrix models that describe this behavior. And on this front, there are plenty of, I've talked about fuzzy sphere so far, but there are plenty of other spaces. And the fuzzy sphere with commutative time is related to the entanglement entropy computations. And there are techniques there that are related to these. They're a little different, but essentially one can try to use similar techniques there and see what happens. And other spaces like fuzzy disk, fuzzy torus, and also this commutative time with fuzzy sphere, there are some numerical calculations for the numerical results, Monte Carlo results for that. and there are some perturbative results for these kinds of spaces. So there's a lot of space to extend the results for fuzzy sphere that I have talked about. But now in my last 15 minutes, I want to shift gears completely and talk about a different multi-trace matrix model. And it's this one. Now, when I've shown you the colorful fixed order model before, this one does look really, really nice and tame. And Badis and his collaborators have looked at this numerically in a little different context. For the motivation is simply that let's introduce the third moment into the probability distribution and see what it does. And for positive t, nothing truly interesting happens because this just increases the energy of the asymmetric configurations. But for negative t, this decreases energy of the asymmetric configurations, and you can expect things happening there. And we just recently managed to get a thing published. I'm just showing this for your amusement. This is a set of the self-consistency equations for one-cut solution. What I'm trying to see that normally for a single trace model without the parameter t here, this would be just an expression for the first moment. But with non-zero parameter t, this is an equation that where C1, where your first moment is a free variable. You need to use this to determine the moments. Now, the equations that come up out of these equations are not solvable analytically. So what you can do is you can scan through your parameter space, and for given parameters G and R, compute the equations numerically. This is different numerics, however, than the Monte Carlo. Yeah, this is just numerically solving equations that are analytic saddle point conditions. So it's not numerics in the sense of Monte Carlo simulations. And what I'm showing you is free energy of blue is the symmetric 2-cut, green is the symmetric 1-cut, red is the asymmetric 1-cut. So you can see there's a phase transition and a triple point where all the phases meet, and the location of the triple point in our calculation agrees with the most recent numerical calculation of the triple point. Now we have been also able to compute some response functions. This is a specific heat of the model for some given G and changing R, and this is even we have been able to compute magnetic susceptibility for those two moments. We have
sorry, what's the coupling of C1 to 3? Is it fixed?
Yeah, it's fixed -1 because you can always rescale it. You can always rescale your parameters, your eigenvalues, and your G and R such that t is 1.
But it's not normalized by m. Even this. Okay.
No, yeah.
Each trace counts as n.
Okay.
Yeah, so this is okay. So this basically this is already in the large n limit because I'm doing the saddle point. If you wanted to compare this with the numerical things, this would be f divided by n squared or something like that. If for finite n, this would be f over n squared. And similarly here. This looks like there could be some non-trivial critical coefficient. We have analyzed this, and it seems that there's the critical coefficient here is 0. That this actually doesn't diverge. It seems that the line goes up quite sharply, but the critical coefficient seems.
Is that first order transition?
Yeah, it's a first order transition, but you see, sorry, I did the. Yeah, the energy, the free energy, the first derivative of free energy is discontinuous. Yeah, and the second Seems to be. Not sure what the problem, what the issue is there, but the critical coefficient does seem to be 0. Okay, but why is this relevant for this conference? I would say because I said that I was going to talk about physics on the matrix membranes, but somehow physics of the membranes is going to creep in related multi-trace matrix models. So as you are probably familiar with, as you have probably heard, non-commutative geometry can be described also in terms of the spectral triples. You have your algebra of functions, you have your particular Dirac operator that determines the geometry of the model, and then you have a Hilbert space where these things act. And when these are finite dimensional, there's a way how to construct fuzzy spaces. You take P Hermitian matrices, Q anti-Hermitian matrices, collect some Clifford module baggage that helps that to work, and you can formulate finite dimensional matrix models that describe some kind of fuzzy geometries. And then you can start doing path integrals over your geometries. Yeah, the Dirac operator D is given by set of Hermitian and anti-Hermitian matrices. So you can let these Hermitian anti-Hermitian matrices fluctuate, and that amounts to fluctuating geometry. And you can do path integrals over that and look for saddles, and people have been doing that. And for the most simple model, you get a multi-trace model that looks like this. So people have tried looking at that numerically. Masoud Kalkali's group have looked also at that using Bootstrap. I'll get back to that soon. And
here the moments here there's simple traces of some scalar field, but what is the scalar field here?
No. Here we have one matrix H, which gives you the Dirac operator on some toy fuzzy geometry. So it's not really a scalar field. It's a way how to describe your Dirac operator on that geometry. So we are now analyzing this model again using numerical technique, just Hamiltonian Monte Carlo. These are some eigenvalue distributions that Samuel has produced. We have analyzed that analytically. This is a free energy of symmetric one-cut, asymmetric one-cut, and various two-cut solutions. And we have even used Bootstrap, where our student has been able to even reproduce some eigenvalue distributions for given parameters. Now, I don't expect you to remember the images that I have shown you. What I want you to remember, though, this is the second piece of information that if you have capacity to remember would be really great. This model has a stable asymmetric two-cut solution. There's a region of parameter G where asymmetric two-cut solution is the preferred one. And something similar has been observed by Mauro in his PhD thesis. And the distribution is just slightly two-cut. For example, for G equal to -6, the filling fraction turns out to be 99%. There's for each one eigenvalue in the one of the minima, there are 99 eigenvalues in the other minimum, but still we do see it both numerically and analytically as a stable asymmetric solution.
Where are the two cuts? I only see one interval.
No, this is a region of G where the two-cut is observed.
So it's a two-cut, but
Let me show you.
acidic.
Yeah, it's like this. Simply, there is a small bump. Yeah, there are 99% of the eigenvalues are here, but we quite certainly see a small fraction of eigenvalues being here. We don't yet know what that means for the geometry of the fuzzy space. This somehow relates, the eigenvalues of this matrix are related to the eigenvalues of the Dirac operator, and the eigenvalues of the Dirac operator determine the geometry of that fuzzy space. We're not sure what this asymmetric two-cut phase means for the geometry of that space. We just, at the moment, we claim the asymmetric two-cut solution is there and is definitely preferred.
It's n independent.
Yeah, this is for n equal to 100. Yeah, you can scale things such that it's independent. There, in other words, there is a reasonable large n.
Do you have actually two-cut solution here with?
Yeah.
You have, and you have also
Let me show it here. For example, here for
a stable two-cut solution, the usual one. You have it.
Yes, we do, but it has higher free energy.
So it's not the middle.
So here you can see all the green dots denote different two-cut solutions, and the lowest two-cut here is an asymmetric. Now, I think that not for all values of G we have all the asymmetric solutions. That here in this region there might be only some two-cut solutions. That not all two-cut solutions all the way to the symmetry one exist. They do exist further away, but we do. What I want, probably the best answer is we observe many different two-cut solutions of various filling fractions, and in this region, the solution with the lowest energy has some strange filling fraction of order of 1%. And so now what we would like really to do is to analyze this model. Well, yeah, remember, this is the number of Hermitian matrices, this is the number of anti-Hermitian matrices. So it's a four-matrix model. There's no chance using the analytical techniques there, because for four-matrix models, there's no chance doing that. But you can do that numerically, and you can probably do that using Bootstrap. And why would that be nice? Because this is the fuzzy sphere. So you could, in principle, analyze a truly dynamical fuzzy sphere, a path integral over different geometries on the fuzzy sphere, and through quantum gravity fluctuations of the geometry, and see what happens there. And question?
Yeah. When the eigenvalues are so much separated, are you able to sample correctly between two?
Samuel seems to be very confident that he can. I'm not the expert in the group on the Monte Carlo things, but I do trust my experts, and he seems that he knows what he's doing. Okay. I have 1 minute to mention one final ensemble, that is gauge theory on non-commutative plane. Now, as you can see, I'm not going even to pretend that I put this. I copied this from Dragan's presentation from 2 weeks ago. Bottom line is that you can use the truncated Heisenberg algebra that we have already seen to formulate a gauge theory model on the non-commutative plane. This model is 3 matrix, phi, A1, and A2. So we have a 3 matrix model that we would like to analyze. Again, using probably the bootstrap techniques that we are currently honing our skills on the Dirac ensemble. And the reason to do that is that there are reasons to believe that even if you use the Grosse-Vulkenaar trick in this gauge theory model, the UVR mixing is still there. That the trick by Grosse and Vulkanar doesn't work for gauge theories for one reason or another. And it would be interesting to see whether we can see some hints about that in the phase structure of this model. And I think it's very nice that I have 13 matrix ensembles in my presentation. I'm going to consider that to be a lucky number in this case. And with that, I'm going to show you the take-home message that I would really like you to remember. And if you have this capacity to remember two more things, then please remember that there seems to be a strange new phase appearing in the model with the fixed external matrix. And there we do see asymmetric two-cut solutions as stable solutions to some multi-trace matrix model. There is some to-do list that I just want to flash here. I've talked about most of those things. And with that, I thank you for your attention.
Great. So thanks very much to Denjo and Jens for organizing and inviting. So it's my pleasure to talk about this topic. I kind of emphasize continuous symmetries here because that's what comes up a lot in known models of holography and ADS CFT. And I'll be talking about how, while there are sort of Lie groups and Lie algebras in the game, finite dimensional algebras play a role, which are kind of directly related to the invariant theory of these continuous symmetries. And then this way of thinking about the problems of invariance of various symmetries in terms of finite algebras also extends to the case where you replace the continuous symmetries by discrete symmetries. It's just that the kind of dual algebras are a little bit different, but this framework for thinking about invariance is quite general. I'll start by talking about the two most recent papers that I'll be focusing on. The one at the very bottom with Adrian Padellaro, who is my recent PhD student, now postdoc in Germany, and Ryo Suzuki, who's a young faculty member in China. So we talk about how to use these algebras and set up some eigenvalue systems on these algebras in order to answer some questions having to do with multi-matrix invariance at finite n. And then the second part of the talk will be about this work with Denjo, in particular this paper where we found how the formulae following from these finite algebras naturally lead to interesting thermodynamics, notably negative specific heat capacities, and how that appears in a control way in certain quantum mechanical systems. Great. So this talk, the physics behind is gauge string duality and ADS CFT. And gauge string duality, we know, from a long time, deep aspect of theoretical physics. Early examples of gauge string duality we know from early 90s, how matrix models through double scaling limits and so on gave us duals for low-dimensional, non-critical string theories. And another beautiful example of gauge string duality was two-dimensional Mills with UN gauge group. The answers, partition functions of these were well known. And then David Gross decided to do the large N expansion of these and see in that large N expansion the combinatorics of surfaces which were covering the surface sigma G where the Yang-Mills theory was defined. And these covering surfaces were interpreted as string world sheets, which form the dual of this gauge theory. So this is a very simple example of gauge string duality. One of the key pieces of mathematics there was Schur-Weil duality, which I'll talk about later, which also plays a role in this story of finite algebras that I'll be describing. Of course, the most famous example of gauge string duality is ADS CFT, and I'll be talking about some problems that arise in thinking about ADS5 cross S5 and its dual four-dimensional super Yang-Mills theory with UN gauge group. So So the broad theme that I'm interested in is, what are the mathematical mechanisms for the emergence of strings from gauge theory or stringy spacetimes and associated branes and things that exist there. So one piece of mathematics that we know from the 90s, very important, localization to eigenvalues. Integrating over matrices, you localize to eigenvalues, and the nice measures that are known. Obviously, in ADS-CFT, the representation theory of superconformal groups, the algebras, are important. ADS-CFT, important developments that allow comparison of weak and strong coupling, integrable spin chains. And there's another piece of mathematics, which is infinite families of finite dimensional algebras. And that's what I'll be talking about. So just to give you the setting of ADS-5 process 5, 4-dimensional CFT and then 10-dimensional string theory. And the 4D is thought of as the boundary of the ADS-5. But where does the S5 come from? It's not evident in the space-time, base space-time of the 4D theory. But the super-YAMLs theory contains 6 Hermitian matrices, n by n, x1 up to x6. And they transform as a vector of SO6, which is in the super algebra, part of the super algebra. And in space-time, SO6 is the isometric group, this emergent S5. So it's clear that the correlators and counting and properties of gauge invariant functions of multiple matrices is going to be important in the study of emergence. So, so the simplest kind of problem that arises in studying half BPS operators is take a complex matrix x1 plus ix2, where these two are the Hermitian matrices. And now think about polynomial functions of these matrix elements, n square variables, let them be holomorphic. And we can organize these polynomial functions by degree, and let us look for things that are invariant under UN, where UN acts by adjoint action. So what do these invariant functions look like? For a moment, let's take n to be large, so larger than the degrees that we're thinking about. So trace z square, products of traces, and so on. And then generalizations of this problem are the ones where you have two such complex matrices. You're still thinking about holomorphic polynomial functions. You have a certain degree in z and a degree in y. So for example, if you have two z's and two y's at different forms of multi-traces you can construct, and even at the single trace level, there's interesting combinatorics having to do with what mathematicians call necklaces, which enumerates the invariants. So, so I'll be talking about both the one matrix, multi-matrix, tensor, and so on. But the important ideas can already be seen in the one matrix case. So you look at degree 3 and think about these invariants, the trace z cubed, trace z squared, trace z, and trace z the whole cube, which corresponds to 3 ways of putting your z's inside traces. 3 equals 3, 3 equals 2 plus 1, 3 equals 1 plus 1 plus 1, which are partitions of the degree. Now, partitions come up in connection with symmetric groups. So is there a more explicit, concrete connection to symmetric groups? Turns out there is a simple and important one, which is that if you want to construct a gauge invariant function, when you write out multi-traces, whenever you write it out in terms of indices, the indices are contracted. So a convenient way to think about all possible gauge invariants of a given degree, let's call that degree little n, is to take little n of your z's, line up your indices I1, I2 up to In in a fixed order, and then everything is going to be contracted. Each index will appear exactly once below, and therefore the indices below will be some permutation of the indices above, which is sigma, mapped from 1 to n back to 1 to n, which is an element of Sn. So for example, if you take sigma to be the cyclic permutation 1, 2, 3, you contract the indices I1, I2, I2, I3, I1, and then you recognize this is trace z cubed. And then if you take 1, 2, and 3, the swap, where 3 stays fixed, that gives you trace Z square times trace Z. So you can construct any gauge invariant operator by choosing a permutation. However, not all permutations give you distinct operators, but that kind of redundancy is itself nicely described by permutations. So it turns out that essentially, if you take the permutation O sigma, the operator O sigma of Z, and you conjugate that permutation by something else in Sn, you get the same operator, the same polynomial invariant function. Just to kind of see what's going on and how to generalize matrices, let's just look at this a little bit more slowly. So if you take sigma to be 1, 2, 3, the index below 1 is 2, the index below 2 is 3, the index below 3 is 1, as indicated by the cyclic permutation, and that you immediately recognize as trace Z cube. If you take 1, 3, 2, 1 goes to 3, so the index below 1 is 3, the index below 2 is 1, the index below 3 is 2. Now, this doesn't immediately look like a trace because there's I1, I2, and I2, I1. But then if you move the Z, the last Z past the first one, the last one past the second one, you get I1, I3, I3, I2, I2, I1, which after relabeling of indices, obviously the same as the one before, which is trace Z cube. Important thing here, you had to move things across, which was kind of something you can also do if you have matrix oscillators. It's also something you can do in quantum mechanics. For example, you have a harmonic oscillator made out of these n-square variables. So essentially, there is a redundancy coming from bosonic statistics, and that leads us to study permutations in Sn, and there is a map from permutations to gauge invariant functions or local operators. You can extend that map from the permutation group elements to group algebra elements, sums over sigma with some arbitrary complex coefficients going to sums of operators in this way. And the equality of invariant polynomials means that there is an important sort of equivalence in the game where sigma is equivalent or in the same equivalence class as gamma, sigma, gamma inverse. So the orbits, so if you think of the gammas as the sigmas as a set of things of interest, the gammas as acting on them, organizing them into equivalence classes or orbits, and these orbits are conjugacy classes. So the gamma is a bit like a gauge symmetry, and sigma is like a bit like a configuration space. So given this conjugacy classes, set of things related by conjugation, here's an interesting thing you could form out of it. Take the sum of everything within a class C with equal coefficients. Such sums commute with anything in the group algebra. So they form part of the center of Sn, Z, C of Sn. And in fact, the center is exactly spanned by these conjugacy class elements. So anything in the center can be expanded in terms of these conjugacy class elements. So, and they form an algebra, because if TC commutes with everything, TD commutes with everything, the product will commute with everything, and then you can re-expand it in terms of the basis, and there's some structure constants, T, C, D, E. Now, these structure constants appear in matrix model correlators. For example, you take the operator O sigma of Z, or tau of Z dagger, do this integral obvious measure on the complex matrices with this exponential Gaussian factor. That correlator is written in terms of the structure constants, and you sum over, so sigma and tau belong to conjugacy classes C and D. You think about those structure constants C, C, D, E, you sum over E, n to the power of the number of cycles in E. So E is a conjugacy class. In Sn, that's the cycle structure. How many cycles? That's the power of n. So it's an exact formula for the correlate. That kind of formula you can also extend if you put a background, so instead of trace Z, Z dagger, take a Hermitian matrix B, trace Z, B, Z dagger. Then in this presence of the background, you sort of see the full structure of these structure constants. You're not multiplying just n to some power, but you're actually multiplying by something that directly is enumerated by those conjugacy classes, namely another matrix invariant. The matrix here is the background matrix. So this also can be generalized to multi-matrices and so on, as done in that paper. So, what's the family of finite algebras that is controlling correlated here? It's the center of C of Sn. N goes from 0 to infinity because we're interested in operators of arbitrary degree. So little n is the degree of the polynomial, scaling dimension of the local operator in CFT4, energy of states in radial quantization in ADS5. Of course, we know in ADS there is interesting physics having to do with the fact that if the energy becomes comparable to n or n squared, things change. So what happens to the family of algebras? Well, each of these algebras has a subalgebra, which depends on capital N. And we just have this infinite family of algebras that depend on capital N. How do we define that capital N dependent family of algebras? Turns out that the this conjugacy class basis that I told you about, you can convert that to a projector basis by taking a linear combination with characters. So R is a representation, this is the conjugacy class, they are paired by the characters, and these linear combinations obey projector-like equations, and R is a representation of Sn, so it corresponds to a Young diagram with little n boxes. And what happens at finite n is that you can just take this projector basis and you can take the projector basis and restrict yourself to projectors associated to Young diagrams with little n boxes, which is now bigger than capital N potentially, but you restrict your Young diagrams to have height no bigger than capital N, so L of R. So, and the reason this works is that this map that I talked about between the group algebra and the polynomial invariants has a kernel, and the kernel is given directly by those projectors which have height bigger than capital N. And this fact is used in constructing the gauge invariant operators, which corresponds to projectors with this constraint. These gauge invariant operators are proportional to Schur polynomials in Z, and they give a useful orthogonal basis of local half BPS operators, which is, has been investigated a lot in the context of giant gravitons. So, so that's how finite n works. And why does it work? Well, it works because of this rather fundamental fact. If you take the fundamental UN representation, capital N dimensional, take the little n-fold tensor product, we had indices I1 up to I little n, so that's something transforming in this tensor product. You can ask how, so the states here look like this. Each one goes from 1 to capital N, so n to the little n states. Natural action of the unitary group, simultaneous action on all the indices. You say, I have this action, how do I decompose it into irreducible representations of UN? There's a direct sum of representations associated with Young diagrams with little n boxes. And so basically for each representation of UN associated with a Young diagram, there's a state label. Typically there'll be a multiplicity label. What this equation is telling us is that that multiplicity label is actually a state space for the corresponding representation of Sn with that associated with that Young diagram. So that's the content of that. And sort of finite n cutoffs naturally arise because this decomposition has a cutoff here. That's just how Schur duality works. And this is a rather general story. There's whenever you have some vector space, some algebra acting on it, you can ask, what is the algebra that controls multiplicities? The algebra that controls multiplicity is the algebra within the endomorphism algebra of this, which commutes with your algebra UN, for example, of interest. And in this case, the commutant of UN is Sn. And whenever you know the commutant, you know the algebra that controls multiplicities in this way, and that's the double commutant theorem. So, similar algebras, the center of Sn that we just talked about, are relevant to multi-matrix problems. For example, two matrices are invariant under simultaneous conjugation. If we are thinking about polymorphic polynomial functions of degree m and n, or you think about a single complex matrix with, now think about non-holomorphic functions with m copies of z, n copies of z bar, same combinatorics. So again, there will be some permutation which will perform all the index contractions. There'll be some equivalence group which will generate, which will tell us which pairs of permutations give the same gauge invariant operator. So these will be the index contraction permutations. There'll be the equivalence permutations gamma, which live in a subgroup of this one, and they act on the sigma by conjugation. And corresponding to these equivalences, you can form orbits, and sums over orbits will give you a subalgebra. This subalgebra will commute with this subgroup, these kind of equivalence generating permutations. So this whole story generalizes to multi-matrices, denses, and so on. Some key properties of AMN, of this algebra that I just talked about, again, just as in center of the group algebra of Sn, there's a conjugacy class basis associated with the orbits, sums over orbits. There's a Fourier transform basis associated with Young diagrams coming from representation theory. Likewise, there's a Fourier transform basis coming from representations theory associated with Young diagrams and some extra multiplicity labels. I'll say more about this and how it's related to sort of structure theory of these algebras. I'll say a little bit more about this soon. Anyway, so this all comes from, so I mean, this picture follows from many pieces of work in the past on D-branes emerging from Yang-Mills, orthogonal bases for multi-matrix systems, and then in this paper with a student, we kind of formalize this notion of permutation centralized algebras and studied various examples and sort of found that it's a rather uniform structure. Yeah.
Did you ever come across a paper, a mathematical paper by Procesi, theory of?
Yeah. So I was just having this discussion with Antal yesterday. So the words that I told you about, they're very much interested in invariant theory of two matrices and so on. So you can look at invariants, let's say for a fixed n, and think about arbitrary polynomial invariants of arbitrary degree. Many beautiful questions there, many complicated ones, what's the Hilbert series and so on. This takes a different approach, a bit motivated by physics. It doesn't fix capital N and look at arbitrary degree, it fixes the degree. How many Z's, how many Y's? Can I find a linear basis? And there's some nice answers to that, which was not the focus of what people were doing in these rings of functions and so on. But there are overlaps, and in fact, the recent paper of Antal is.
So my egoistic question is whether you understand that paper. I try to understand it.
Oh,
do you understand it?
I understand enough to know that it's not answering the question I want to be answering. Okay, very good. So there are these algebras. And the main, some of the recent work has to do with how you apply these algebras to use them to arrive at some efficient algorithms for constructing bases, orthogonal bases in some natural inner product from quantum field theory for multi-matrix invariants of finite n. That was the second paper at the bottom. And then also how the counting formulae following from algebras like this lead to interesting physics of negative specific heat capacity, which are of interest in the context of small black holes in ADS-CFT. And then, so here and here, I'm still focusing on continuous symmetries, but then, in fact, same kinds of universality classes of phase transitions and so on occur when you replace UN with Sn, and that's one motivation to think about Sn as a gauge symmetry. And then I'll say some things about that. So if there are any questions at this point, I'm happy to pause and take some questions, then I'll go to the gist.
So the motivation for introducing sure operators is because they are orthogonal under the point function.
That's one important physical motivation, yes.
Is that the same as you showed here? You introduced projection.
That's the projectors. Essentially, there's a way to derive that orthogonality that follows from the orthogonality of the projectors.
So the same logic operates for the multi-matrix case.
Absolutely. So there'll be a projector-like basis, which will have nice finite end cutoffs. And you can, this map that I described from the algebra to the invariants works in the same way. And then you get orthogonal basis for those operators. And that's what was shown in these papers that I list here. These papers here. Diagonal multimatrix correlators and so on. So I mean, I'll tell you with the motivation for the current work, why we want algorithms and so on. So just a little bit about these two matrix invariants. So same idea. You have m copies of z, n copies of y. So there's a typo here. This z should be a y. So a string of z's and a string of y's. The indices lined up from I1 to im plus n. There's a dot, dot, dot here as well. And then a permutation in Sm plus n, which performs all possible index contractions. And there's now a bosonic symmetry of permuting the z's while permuting the y's, which is a symmetry. You're replacing the z with the z. So up to renaming indices, you'll get the same thing. And you can use that to show that if you have this gauge invariant polynomial built from sigma in Sm plus n, and you conjugate it, but with a subgroup element in Sm cross Sn, you'll get the same operator. If you conjugate with a more general thing, you won't necessarily get the same operator. I mean, you won't in general. And you can show that the one-to-one correspondent with the different gauge invariant operators and these equivalence classes under subgroup conjugation. Again, when you have these subgroups and you have something in the bigger group, you can form averages under conjugation. There will be sums over elements in these orbits under the group action, and these sums will commute with these elements in the subgroup. If you multiply by mu here, you get a mu here, as a mu here, mu here. You can absorb it by redefining gamma, and the mu comes out on the other side, so it commutes. So this will be a subalgebra of the group algebra of Sm plus n, which commutes with this subgroup, or the corresponding group algebra, which sits as a subalgebra inside. So basically, AMN is a subalgebra which has this characteristic. It commutes with this. There's a nice basis given by these orbit averages, but that's not the only thing. It has another basis. Basis of what sort of algebra people call matrix units. So essentially, you should think of it as, okay, here's a complicated algebra. And here, this triple here, R1, R2, is labeling blocks, matrix blocks within this algebra. So matrix blocks in the sense that if you multiply Q, R1, R2, mu with Q, R prime, R1 prime, R2 prime, alpha beta, you're going to get 0 unless R equals R prime, R1 equals R1 prime, R2 equals R2 prime. And then these will multiply like elementary matrices as delta nu alpha, and then R1, R2. So you contract these indices and nu beta. So they obey this kind of generalization of the projector equation, where there's kind of matrix-like multiplication. And this arises because, unlike the center of the group algebra before, this one is a non-commutative algebra. So So the algebra, it commutes with everything in the subgroup, but doesn't commute with everything. It doesn't commute with itself. So what are these R1, R2? They are Young diagrams with m plus n boxes, m boxes, n boxes. And these indices go from 1 up to the Littlewood-Richardson coefficient. So R1 is some Young diagram, let's say, if n equals 3, n equals 2, R2 will be a Young diagram with 2 boxes, for example, this, and there's a Littlewood-Richardson rule, says how you can combine Young diagrams. So R could be something like this, where you can put these two together. In general, for a given Young diagram here, there could be a multiplicity, and that's what I call G, R1, R2, R. And the two indices that go over that range from 1 to the Littlewood-Richardson multiplicity. Now, there are expressions for these things in terms of physicist group theory things like the matrix element of permutation sigma of Sm plus n inside some representation with Young diagram with m plus n boxes. There are old algorithms for constructing these things. They're hard, Young Yamanouchi symbols. There's analogously branching coefficients. Take a state in this representation R, take a state in this subgroup representation, find a way to construct a basis, find a way to describe the multiplicity, take these overlaps. These are branching coefficients. In principle, there are ways to do this. So you can write a formula for this in terms of these things, and these things naturally come with orthogonality properties, and that's why you can prove this kind of identity. But actually building such a thing is not easy, as many of us know who have worked on these things. So David, among others, one of the inventors of this concept. So, the other power of this algebra is that finite and cutoff is easy. It just follows from Schuval duality. That big Young diagram with m plus n boxes, you just cut it off. Keep only these matrix elements. Again, this follows from Schuval duality, namely that you have m plus n tensor factors and have u tensor m plus n. It'll be dual to this group algebra. If you have two unitary group elements, one acting m-fold way, another acting n-fold way, the dual algebra is this algebra. So when you use all of that, you get the correct description of finite and invariants in terms of this. So this is finite and counting. But anyway, so we still haven't constructed this. So we were recently interested in how do you go about really explicitly building these things. So you take advantage, essentially, the fact that this algebra has two bases. One is this permutation orbit type basis, and the other one is this Q basis, which is hard to construct. But what you can show using these formal expressions, that if you take some central elements in Sm plus n, namely some sums over conjugacy classes labeled by some cycle structure in symmetric group Sm plus n, you take such a thing, you multiply with the Q, you're going to get some number, a normalized character. So this is ordinary Sn character. You can look it up in tables, and you get back the Q. So these guys are actually eigenspaces. They form eigenspaces where the eigenvalue depends only on this R label. So R was the representation of the m plus n boxes, corresponding conjugacy class element. You get these guys. If you take R1 here, it was a Young diagram with m boxes. So take conjugacy classes in Sm, analogous character equation, which detects R1. And this one, if you take n boxes here, corresponding conjugacy class element, a normalized character. So again, formally using the formulas, you can prove this. But again, it's not that useful yet because the Qs are not easy to construct. However, you know that both the Qs and these orbit elements span the same space. So you can think about these eigenvalue equations in this combinatorial basis, in this orbit type basis. To take any of these central elements labeled by some partition, you multiply that. You can do that in sort of mathematical software like Sage and stuff like that. You can just tell it what you want to multiply. You can generate these orbits using this kind of software, and you'll get a linear combination of these orbit elements and some matrix, which corresponds to that central element you are interested in. And you know that you're looking for things which are eigenstates of with some particular eigenvalue, and these eigenvalues are known. So basically, you're looking for eigenvalues of this matrix, and you're trying to solve this equation. Find vectors such that this minus this eigenvalue is going to give 0. So you're looking for null vectors of these matrices. Turns out that nice thing is that these are integer matrices. These normalized characters are integer matrices. So it's all boils down to finding null vectors of integer matrices, for which there are nice algorithms, Hermite normal forms, and other efficient things. And so you look for null vectors of a system of equations labeled by these these sets of eigenvalues, which will kind of, if you were to use all the p's, sorry, this was a q here, p, q, and now if you use all the p's sort of central elements here, you would kind of pin down what is R1 and what is R2, but you haven't pinned down mu nu. So you get a multiplicity of vectors, but because they're coming from solving some eigenspaces of Hermitian operators, you got some naturally some orthogonal, your algorithm will give you some orthogonal basis of G squared. Yes.
So what are the D's, the sum divisors of the character?
So the D's, so there is a representation of the symmetric group associated with this Young diagram is the dimension of that. So the factorial over the hooks. So basically, using this, you can get the a multiplicity of vectors which are orthogonal naturally from the algorithm. And this kind of thing, we have set it up out. So what makes it efficient? I mean, still, you know, let's say you have 15 elements, or sort of a degree 15, let's say 8 Y's and 7 Z's or something. Then you're dealing with S15. So naively, if you look at that system of equations, you're still dealing with central elements, partition, cycle structure in S15. So number of partitions of 15 is a big number. But there's a nice little fact about group theory that makes this efficient. What it is that, so what we're trying to do is distinguish the Young diagrams in some symmetric. And we're going to distinguish them using some set of eigenvalues of some conjugacy class elements, which are related to characters. Well, it turns out that it suffices to choose a few conjugacy classes, you know, and in fact, you can restrict your attention to cycle conjugacy classes, where these have exactly one cyclic permutation of length 2 and everything else is left fixed, one cyclic permutation of length 3, everything else is left fixed, up to a certain maximum cycle length. And this maximum cycle length grows very slowly with n. For n up to 14, it suffices to just use 2 of them. So basically, just look at the normalized characters of these 2 conjugacy classes, look at the character table, look at the normalized characters. No 2 representations, no 2 irreducible representations will have the same pair of eigenvalues. So therefore, you can just use, in setting up your eigenvalue systems, you just have to use this. And this has a nice algebraic meaning in the sense that these subsets form a kind of a non-linear basis in the sense that powers of this, appropriate powers of this can be used to write any projector as a linear combination of things. So the connection between detecting Young diagrams and nonlinear generating set, it's a simple proof. And we have explained this and we have looked at the data such as this one. If you're working with symmetric group up to 80, you only need to go up to T6. So there's some neat thing going on about how cycle operators know about complicated symmetric groups. So great. So far I've talked about AMN, combinatorial basis, that leads to nice counting formulas. The dimension also follows from the basis. You have triples of Young diagrams, you have squares of Littlewood-Richardson, and this knows nothing about capital N. And if you want to get a finite N answer, finite capital N answer, you just have to restrict the length of this Young diagram to be less than or equal to n. So it's a very simple cutoff in the Q basis. There's no known simple cutoff in this combinatorial basis, which is partly what makes invariant theory hard. Invariant theory of multi-matrices hard. There's no, in this combinatorial way of thinking about these algebras, there's no simple way that is known for cutting off finite n. But in the Q basis, in the Fourier basis. So what can you do with these finite n formulas? In particular, you can look at m equals n, so two matrices, for example, in physics, Z and Z dagger, zero charge because this has charge +1, this one -1. So you look at a special case where R1 and R2 have the same number of boxes and so on. This is a state counting of matrices. You can also do a corresponding state counting in the matrix harmonic oscillator. So it's a very physical counting states with energy 2n. Each Z is an oscillator, each Z dagger is an oscillator. And you have an energy, you have a multiplicity, which is log of the multiplicity is the entropy. And using, spending a year here in DIAS, you learn a bit of thermodynamics. So how to do interesting thermodynamics with this. So these numbers, Z of n counting states. Well, first of all, there was a paper with postdoc Zahavi and mathematician Mark Wilson, where we worked out how does this thing grow in the sort of large n limit. Still, forget about capital N, just this large energy. So there's an interesting 4 to the n over root n, and this is in the denominator, which is important. Now, this kind of growth of degeneracy, so now you have the thermal partition function, e to the minus beta times the energy. You have this coming from there. And now if you compare these sort of leading exponential parts, you see that if beta is small, then this positive part will dominate and there'll be a Hagedorn transition, which is very similar to what you see in the pure matrix model without restricting the two matrices to be equal in number, just any number, but just fix the total number of matrices. That is a well-known Hagedorn transition. So here there's a Hagedorn transition likewise. But if you use these finite n formulas, entropy as a function of finite n, microcanonical ensemble, temperature is derived using ds by the energy, so inverse temperature ds by dn. And you can just plot this temperature versus energy is just n. So you plot this and you find this is an artifact of not very generic stuff having to do with small n. We're interested in little n being large. So you have kind of a negative, this is energy versus temperature. So as energy is increasing, temperature is decreasing, and then it goes up. It's not too easy to do these computations with the group theory formulas for large numbers of Young diagrams and so on. So up to 13, 18, you can do things. And you can see, though, that this negative branch increases in size, and there is a turnaround at order n square, and then maybe n squared over 4. This kind of turnaround in the two matrix case has been studied by David Berenstein and Genjo. Similar things in this two matrix with constraint on Z and Z dagger, and then you have this negative part which turns around to be a positive specific heat. Again, we can extend this stuff, very similar phase counting and phase transitions when we have not matrices, but let's say 3 index tensors, which is of interest in tensor models, phi ijk, phi bar ijk. You can build invariants by contracting the holomorphic and anti-holomorphic. If you have multiple phis and multiple phi bars, again, you have permutations that tell you which index you're contracting with which. And there's some equivalence having to do with the fact that these are bosonic variables. So you get essentially triples of permutations because there are 3 indices. You get 2 equivalence generating permutations from the phis and the phi bars. And this amounts to studying these equivalence classes are a double coset, in fact. And there's a double coset algebra where you have a product of SNs divided by the diagonal part of SN on the 2 sides. And these algebras, the dimension grows rapidly, n factorial. So you have analogous entropies log n factorial. and using this very simple microcanonical thermodynamics, you can see that log n factorial leads to negative specific heat capacity. Here, the growth is much faster than exponential in n, n log n, because n factorial. So basically, for no finite beta, will this converge as n goes from 0 to infinity? So essentially, this is what people call a zero. So in the previous case, it converges for low temperature and then diverges. In this case, it doesn't converge at all. So people call this zero temperature Hagedorn, which was identified by Klebanov and Seitlin. And you can see that, how that with the finite n counting, how this negative specific heat exists, and then it turns around. Now, the same kind of behavior can be seen without 3-index tensors, just matrices, by reducing your UN gauge symmetry to SN gauge symmetry. And the advantage of doing that is then you have still group theoretic and analogous formulae. But then in that case, because in some sense, sometimes finite groups are easier to deal with, and then you can actually write the canonical partition function and then study everything in the canonical ensemble. So that's what we did with Denjo last year in that paper I mentioned. You have a matrix X, invariance under U, X, U transpose. U is an n by n permutation matrix. And you can ask, how do I count invariance of this matrix under this invariance? And how do I sum up the invariance for all degrees to get a generating function? This is a problem that depends on capital N, on X with e to the minus beta. The answer comes by thinking about some results from invariant theory, the Mullier-Weil formula. The answer comes as a sum of a permutation partitions, which are conjugacy classes of Sn. And then there's something, a determinant of something having to do with permutations. And then you know enough about determinants of permutations, matrices in these representations to actually simplify this substantially. And you get that this canonical partition function is a sum over partitions, 1 over symmetry factor associated with that partition. And then this very interesting function here, which depends on capital N, a partition, and little x, which has to do with the temperature. This thing is this product. So you have a partition which has some number of cycles P1 of length A1, some number of cycles P2 of length A2, and so on. So you have a set of cycle lengths A1 up to AN, sorry, A1 up to AK, indices 1 to K, labeling the cycle lengths. So take a pair of indices I and J which can live in the set 1 up to K. So basically you pick a pair, and then you look at the LCM, least common multiple of the pair of cycle lengths, and you take 1 minus x to this power, and then that whole thing to the power, which is the product of those cycle lengths divided by the LCM, which is an integer, times pi pj, which is the multiplicities of those cycle lengths. And using that, you can study thermodynamics in detail in both the micro and the canonical ensemble. In the micro, you get negative, positive, there's a turnaround at interesting scale of n log n over 2, apparently, from the numerical data. And then you get sort of a turnaround having to do with finite n effects. And then turns out negative specific heats can only be observed in microcanonical ensemble. There's a simple argument that in the canonical ensemble, the specific heat is a dispersion and therefore must be positive. And our results are all consistent with that. Here I have plotted temperature, energy. This is energy in the micro canonical ensemble. There's this negative branch, but in the canonical ensemble, it's always, the gradient is always positive. And then you at some point, you recover n square harmonic oscillators where things behave in a very traditional way. And this, in the canonical ensemble, we have explicit formulas for canonical ensemble. So you can look at this energy temperature curve. You can look at the specific heat capacity. You can plot those as a function of capital N. So N equals, I think, 10, 15, 20. So you can see that the place where this very rapid change is happening is decreasing in temperature. And we can actually derive a formula for where this happens. It's order log n over 2n. And the way we derive it is we go back to this exact product form, and we use the product form to figure out the high temperature expansion. Then we look at what are the two leading terms in the high temperature expansion. When do they become comparable? That's when the high temperature expansion breaks down and you get a scale.
Is this what you mean by the microcanonical ensembles?
This one was micro.
If you go to the slide before that, I mean,
Yeah.
what is this is the formula for the microcanonical?
This is for the canonical ensemble.
And what's the how do you compute the microcanonical ensemble?
So actually, you can get the from this one. Basically, you expand this in powers of x, and the coefficient of a given power is the degeneracy x. So the coefficient of x again is the z, and the little n term over little n is what I call z and the x. So actually, this is a very efficient way to get this, because you have a nice formula for this. You just expand this product, and then you look at the coefficient. So that will give you an omega of n, omega of the energy. So that those formulas.
The microcanonical.
Yeah, that's the mic. Yeah, because it's state counting times e to the minus beta n. So there are two things you can do. You can derive a temperature from this guy, call this entropy, S equals log omega. TdS is du. So ds by du is 1 over t. So that's a t micro, where I'm using this S defined as log of omega. Or you can just plot this thing as a function of x. So x is the e to the minus beta. So there are two things you can do, and you can compare. And that's what we did here. The blue one is the canonical ensemble, where every specific should be positive, and this one is from the degeneracies themselves. So yeah, maybe just final thing to say that these calculations of these canonical partition functions can be extended from matrix case to tensor case, as we did recently, very recently. And this product form has a very nice generalization. You take S index tensor, you get S indices going from 1 to k, which are labeled the cycle lengths. You get the LCM of these guys, and you got a product of these cycle lengths, product of the multiplicities, and again, from that, you get similar thermodynamics. There's even a nicer way to write it, where the S dependence just appears in simple exponents of integers. So if you're interested, the code is in the paper. You can play with it on Mathematica and investigate physics. So I think I'm close to the end. So is that right? I think I'm close to the end, right? Yeah. So to summarize, so we have a bunch of thought about a bunch of problems having to do with polynomial functions of matrix and tensor variables of size n, which are invariant the symmetries UN that come up in ADS CFT. And these problems are usefully approached by exploiting dual families of algebras. This is the two matrix case, but different cases, and always families organized by the degree of the invariance you're thinking about. And the key elements are you're going to contract indices to form invariants. So you use permutations to parameterize the index contractions. Not all permutations give distinct operators, so there are some equivalences. These are themselves generated group theoretically by permutation acting on permutation. And these equivalences follow from bosonic or fermionic statistics. And corresponding to these equivalences, generalizing the notion of conjugacy classes, there are associated equivalence classes and associated algebras. And when you want to do finite n effects, you go from this permutation bases to some representation theory basis, which is possible thanks to Chauval duality, and you get useful finite n information, counting thermodynamics, correlators, orthogonal bases, stuff like that. I didn't say too much about the dual algebra when UN is replaced by Sn. There's also a dual algebra. These are partition algebras. They have been used with my student Padellaro and Barnes to study physical things like large N factorization of observables. Partition algebras are very nice. They are just to motivate you to have a look if you are interested. Essentially, symmetric group, let's say S3, 1, 2, 3. It's a map, sigma of 1 goes to 2 here, sigma of 2 goes to 3, sigma of 3 goes to 1. So that's the 1, 2, 3. You can represent permutations using diagrams. And when you go to, so these kind of permutation algebras are dual. They organize the invariants in UN problems. The UN degree K, let's say degree 3. You are thinking about S3, like a dual algebra. If you replace this gauge symmetry with Sn, and then you say degree K, for example, 3, you have another algebra which is P3n. And what that algebra looks like, it has a basis of, in terms of diagrams, it's just slightly more general diagrams. So you can have these guys. You can also have some nodes that have nothing coming out of them. You can have some nodes that are connected from the lower line to the lower line. These are partition algebra diagrams. And there's a way to compose these diagrams. And when you compose them, sometimes you get loops, and you just set the loops. You can simplify the composed diagram to it's this kind of diagram again, n to the power of number of loops. So n actually enters in structure constants of the algebra. So this kind of algebra is what helps you to develop analogs of these QR, R1, R2. This representation theoretic stuff will be representations of this dual algebra. So yeah, I'll stop here.
So this, first of all, I would like to thank the organizers for inviting me to this workshop. So I wanted to be there in person, but unfortunately, it didn't work out. So let me begin my talk. So this is an ongoing work in collaboration with Arpit and Piyush. Arpit is a postdoc at CCNU in China, and Piyush is doing his PhD at Wuppertal. So let me begin with the complex Lanchman method, an overview, and stochastic quantization. So complex Lanchman dynamics with stochastic quantization, it is a modification of path integral quantization. So we have the Euclidean path integral measure, which is given by this 1 over the partition function times exponential of minus s. So we can interpret this as an equilibrium distribution of a stochastic process. So how do we implement this?
Your pages are not showing. Your pages.
It's okay. So let me share again. Okay, are you able to see the slides?
Yeah, yes.
Yeah.
Okay, all right.
Yes, it's moving now.
Okay, yeah, thanks for telling me. Okay, so the question is, how do we implement this complex Lanchman dynamics? So we can make the system evolve in a fictitious time subject to a stochastic noise. So the evolution happens according to Lanchman dynamics, which is given by this equation. So this is the Lanchman equation. So here we have the rate of change of a field, say a scalar field. Here x is space-time coordinates, and theta is the Lanchman time. So this the dynamics contains the gradient of the action with a negative sign, and there is a noise as well, which is a Gaussian noise. And this noise obeys certain constraints. Its average has to be 0, and its 2-point function should obey this relationship. Now let's consider a toy model in 0 plus 1 0 dimensions, which is space-time, which is where space-time is just a point. So we look at this particular form of the action. Here phi is a scalar field, and sigma and lambda are couplings. So Langevin dynamics for this field, it has this particular form. And if you look at the first term, which is the gradient of the action, it is called the drift term. It is similar to friction in analogy with the Brownian motion. And the noise, it is a kick term. It is imparting random kicks to a particle, for example, in Brownian motion. And the noise obeys these constraints. Now, the stochastic evolution, it generates the scalar field phi at a given Langevin time theta with a probability density given by this P of phi comma theta. And this probability density, it is also evolving. It evolves according to Fokker-Planck equation. So here is the evolution of the probability density, and LFP is the Fokker-Planck operator, which is given by this. Now we can compute the expectation value of an observable, which is given by this. So here O is an observable which is made out of the scalar field, and P is the probability density. And we can compute the expectation value in this way. And let's assume that ergodicity is valid in the system. Then we can show that in the large Langevin time limit, the probability density P, it approaches the Boltzmann weight, which is given by this 1 over Z times e power minus S of phi. So this is the same as Euclidean path integral measure. Now we can compute expectation values of observables in this way when we do Langevin simulations. So here on the right hand side, you can see the figure where we have a typical observable. So we can start from anywhere, and eventually this observable will find its equilibrium value and it would fluctuate around there. So similar to what we do in Markov chain Monte Carlo, so we can remove the initial part and we can take the average of the equilibrium fluctuations and the corresponding error to get the physics observables of the system. So as an example, let's look at the evolution of the scalar field given in this action. So the action has this particular form. So sigma and lambda are 2 parameters. And in this particular case, it is just an integral that we can solve easily. And for the correlation functions or powers of the field phi, we have this expression gk, which is phi power k, expectation value. So we can compute this integral and we get some gamma functions and cosine. So here on the right hand side, you can see that the complex field is evolving in Langevin time, and eventually it settles down to a point in the complex field plane, and it fluctuates around there. So it arrived its equilibrium distribution and it fluctuates around that point. So here we can see the analytical value, which is given by this G1, which is the analytical value, and the line below we can see the result obtained from complex Langevin simulations. So they are kind of agreeing within error bars. I am not showing the error bars here, but there are error bars. So this is one simple example of the application of Langevin dynamics. Now making Langevin complex. So in the previous example, I mentioned that real Langevin dynamics, but I gave an example of complex Langevin dynamics. So I did not get enough time to put in a real Langevin dynamics example, but it conveys the idea. Now making Langevin complex. So this is a formal extension of real Langevin dynamics. So it was introduced a long time ago. So we can extend the real field variable into the complex plane. So what we have is a real part of the field and an imaginary part of the field. And the observable is also extended into the complex plane. So here noise becomes complex. So it has a real part and an imaginary part. And the stochastic equations, they take these two forms. So there are two Langevin processes. One is for the real part of the field, and the other is for the imaginary part of the field. And we have the gradients of the actions as well, given by this on the right-hand side. So the noise terms, they obey these constraints. So these are similar to the constraints we saw for the case of the real Langevin dynamics. So here we introduce certain constants, nr and ni. So they should obey this constraint, nr minus ni equal to 1. So in practice, we can take nr equal to 1 and ni equal to 0 and do the complex Langevin simulations. So coming to the expectation value of the fields, we can have two kinds of expectation values. We can express the expectation values of an observable O in two different ways. So one is take the probability distribution which is real, which is a two-dimensional probability distribution, and do the integral and find the expectation value. And the other is take a complex distribution. So it has no interpretation as a probability distribution, but it's a complex distribution for the real field variable phi. So this observable is made out of the field phi, which is real, and the integral is over the real field. So as I mentioned before, this probability distribution P of phi r, phi I, it is a two-dimensional distribution, and it is a real positive probability distribution. And we can obtain this observable O as analytic continuation of the original observable, which depended only on the real field phi. Now, this probability distribution obeys Langevin dynamics. So here we have the Fokker-Planck operator, which is valid for the real and imaginary parts of the fields. So it takes this particular form. Now, coming to the second expression, where rho is the complex weight and phi is an observable made out of real field. And the density rho, it obeys another Fokker-Planck type of evolution, which is given by this. So here we have the complex Fokker-Planck operator, which is given by this. So in the large Langevin limit, it can reduce to exponential of minus of the complex action. Again, here we cannot interpret this as a probability distribution because the exponent is complex. Now, complex Langevin is justified if these two expectation values are the same. So we get from the two-dimensional real probability distribution and the expectation value we get from sampling over or integrating over this complex weight. So this suggests that there is a relation between the spectra of real and complex Fokker-Planck operators. But this constraint is, this condition, which this equation is not yet proved in full generality. So in the derivation, there are boundary terms, and one has to take care of those boundary, the surface terms and things like that. Now, it is extremely difficult to find the stationary distribution, the two-dimensional distribution. However, we can apply certain correctness criteria to justify the use of complex Langevin method. Now, let's move on to some applications. So let's begin with some simple models with supersymmetry. So let's look at supersymmetry quantum mechanics. So consider a theory in one dimension. So we have time as one dimension. The degrees of freedom are a boson and fermions. So we can introduce an auxiliary field B, which has no dynamics. It has no kinetic term. The Euclidean action of this theory, it has this particular form, and here W is the superpotential. The action has a symmetry, as can be seen from the form of this Lagrangian. So this is supersymmetry. So there are two supersymmetry charges, Q and Q bar, and the action is invariant under Q and Q bar. So as shown in this equation, in these two equations. We can write the partition function in this way, exponentiate the action. So this is the Euclidean partition function. So the question is, even though the action is supersymmetric. Is it broken spontaneously, or is there a dynamical supersymmetry breaking in the system? So to see that, we need to study the system non-perturbatively. So we can put this on a lattice and simulate. So the action can be complex in general, coming to the form of the superpotential. So we can have complex superpotentials as well. So we resort to using complex Lange-Van dynamics. If the action is real, we can use Markov chain Monte Carlo and get some interesting results. So let's put this theory on a lattice. So we have a one-dimensional lattice. So it contains T number of equally spaced sides with a lattice spacing A. The physical extent of the lattice is given as beta, which is T times A. So we replace continuous derivatives with difference operators. So here is the lattice action of our theory. So one can derive this and get this particular expression. So here this nabla is the symmetric difference operator, then omega prime and omega double prime. So they are terms containing superpotential and also Wilson mass terms. So there is a particular type of discretization on the lattice. So this lattice action respects Q supercharge, but it does not respect the other one. The Q bar supercharge is broken on the lattice. Now, when supersymmetry is broken, the partition function vanishes. Then expectation values of observables normalized by the partition function could be ill-defined because the denominator is 0. So we need to overcome this difficulty. So what we can do is we can apply twisted boundary conditions on fermions. So we change part of the boundary conditions. So we apply periodic boundary conditions for bosons and twisted boundary conditions for fermions. So for that, let's introduce a twist parameter, which we denote as alpha. Now, applying twisted boundary conditions, the bosonic fields are unchanged. So the field at site T is the same as field at site 0. But for the fermions, it comes back with a phase. So e power I alpha for psi and e power minus I alpha for psi bar. And the partition function on the lattice, it takes this particular form. So there will be a summation over all fields at each lattice site. And so we have exponential of the action with the twist parameter here. We can compute the expectation value of an observable in this way. So here we insert the observable into this expression, and we can compute the expectation value. Now there are other observables. So these are mass gaps, computing the mass gaps from 2-point functions. So we have bosonic and fermionic correlation functions given by this. So we can extract the mass gaps using exponential fits to these 2-point functions. So there is another observable, which is the auxiliary field itself. So we can use that to predict supersymmetry breaking. So if this auxiliary field, if it is not 0, its expectation value, then SUSY is broken. And if it is 0, then supersymmetry is preserved. So we can use the bosonic action also to monitor supersymmetry breaking in the simulations. So bosonic action, we expect it to be half the number of sites. If it deviates away from half the number of sites, supersymmetry is broken. Otherwise, it is preserved on the lattice. So now we can look for other observables which are word identities. So we can introduce source terms, and we can vary the partition function and get some constraints between fields. So here is a word identity which connects the bosonic and fermionic correlators in this way. So we can use this word identity as well to investigate spontaneous supersymmetry breaking. Now let's do some simulations. Let's look at the simple case, which is a double well potential in this model. So let's consider this potential, which is a real potential. So supersymmetry is broken in this model. We can also consider a complexified version of the double well potential, so which is a purely complex potential. And we can ask whether SUSY is broken dynamically in this model. So here are some simulation results. So here we are looking at the auxiliary field observable B against Lange-Van time and for the double well potential. And we see that B does not fluctuate around 0. So the real part is 0, but it has a non-zero imaginary part. So supersymmetry must be broken in this model. And another indicator is the expectation value of the bosonic action. So it is also some huge value. It is not 1/2 of the lattice sites. So here the number of lattice sites is 8. So we should expect something similar, close to 4, but that is not the case here. So supersymmetry is broken in this model. So now moving on to complex double well potential. So here also we can look at our simulation results. So here the auxiliary field, it is fluctuating around 0. So we can take the average of this and we get something close to 0 plus or minus some error value. So the auxiliary field fluctuates around 0. So supersymmetry is unbroken. It is suggesting that supersymmetry is unbroken in this model. So we can look at the bosonic action as well. It is fluctuating around 4, which is half of the number of sites, again suggesting that supersymmetry is preserved in this model. So we can look at word identities. So on the left-hand side, we have the real double well potential. So clearly we can see that the word identities are not satisfied. So SUSY is broken in this model. And on the right-hand side, we have the complex double well potential. And here the word identities are satisfied, so which is suggesting that supersymmetry is preserved in this model. There is no dynamical SUSY breaking in this model with complex double well potential. Now moving on to other types of models with a certain kind of symmetry, which is known as PT symmetry. So these are non-Hermitian quantum theories with PT symmetry, but the spectrum is real, even though the action is complex. So we can consider this specific type of superpotential. So here delta is a continuous parameter. The supersymmetric Lagrangian, it breaks parity symmetry. We can ask the question if breaking of parity induces a breaking of SUSY in this model, a dynamical breaking or a spontaneous breaking. So this question was explored for the two-dimensional case in a two-dimensional supersymmetric model using perturbation theory by Bender in 1997. And perturbative analysis showed that supersymmetry is not spontaneously broken in the system. So we can study this model on a lattice using complex Langevin method and look for dynamical SUSY breaking in this model. So here are some simulation results. On the left-hand side, we can see the auxiliary field against Langevin time. And for the parameter delta equal to 2, and below we see the parameter delta equal to 3. Again, it is fluctuating around 0, but there are huge deviations. And on the right-hand side, we see the bosonic action for delta equal to 2 and delta equal to 3. So they are giving, so it is fluctuating around 4 because t equal to 8. So what we expect is t by 2, which is 4, if supersymmetry is preserved in the system. We can look at word identities as well. So we see that word identities are satisfied, suggesting that supersymmetry is preserved in this model. Now, so these were some simple examples. So we are moving on to reliability of complex Langevin method. So this is a numerical approach, and there are no rigorous analytical proofs available. And how do we check if the simulations are reliable? So we can look at the probability distribution, the two-dimensional probability distribution. So it should decay sufficiently fast in imaginary directions. So there are correctness criteria which are given by this. So one is we can use Fokker-Planck equation. And the other is we can check how fast the drift decays. So if you look at the correctness criterion based on Fokker-Planck equation, so the holomorphic observables of the theory at lattice site k, it should evolve in this particular way. So here Lk is the Langevin operator at kth site, which is a complex operator. So once equilibrium distribution is reached, this d by d theta, there shouldn't be any theta dependence because it has reached equilibrium distribution. So then L tilde acting on this operator should be 0. So it should fluctuate around 0. So we can use this as a criterion for correctness of the complex Langevin method. So in our case, we can take the auxiliary field itself as the observable, and we can see how this observable behaves with Langevin time. So here is a plot for this delta equal to 3 model I introduced earlier. So here this L tilde acting on B, it is indeed fluctuating around 0. So which is a correctness criterion. So it must fluctuate around 0. So telling us that Langevin method is valid. So here also we see for delta equal to 4, again there are deviations from 0, but overall it is fluctuating around 0. Now, another correctness criterion is decay of the drift terms. So we can look at the probability distribution P of U, where U is the magnitude of the drift term, which is given by this square root of the gradient of the absolute value of the gradient of the action, and take the average over lattice sides, take square root, and we look at the probability distribution of U. So this distribution should be suppressed exponentially at larger magnitudes to guarantee the correctness of the complex Langevin method. So here also from the previous examples, we are looking at how the probability distribution decays for large U. So we are seeing that it's decaying exponentially or faster for these models. So this is also another test. So this is the second test to check for the correctness of the complex Langevin method. Okay, now let's move on to the next application, which is the main, which is the title of the talk. So we are looking at spontaneous symmetry breaking in IKKT matrix model. So IKKT matrix model, it was proposed as a non-perturbative formulation of superstring theory back in the days in 1997. So the name is coming from these authors of this paper. So here space-time emerges dynamically from eigenvalues of bosonic matrices in the large n limit. So we can study the scenario of dynamical compactification as a purely non-perturbative effect. So this model, it contains a description of an arbitrary number of D objects. So here in a matrix, the block diagonal entries are D objects, and the off diagonal entries, they represent interactions between these D objects. Now the age-old question, it is why there are 3 large spatial dimensions. So can this model give some hints about large spatial dimensions? So in string theory, what we know is the extra dimensions, they have to be compactified because we don't see extra dimensions in our everyday life, only 3 large spatial dimensions and 1 large time direction. So IKKT matrix model, where is this coming from? So it is coming from dimensional reduction of the 10-dimensional supersymmetric Yang-Mills theory to a point. So here space-time is a point. So we take n equal to 1 super Yang-Mills in 10 dimensions, and we dimensionally reduce that theory all the way down to 1 single point. So the model contains a large number of matrix degrees of freedom. So there are scalar fields, 10 scalar fields and 16 fermions, and these are all n by n matrices, and we are looking at the large n limit of this model. So here is the action of the model. As you can see, since space-time is a point, there is no integral in this model. So we are not integrating over anything. So here, this is the bosonic part of the action, this is the fermionic part of the action, and here we have G Yang-Mills, which is suggestive of the dimensional reduction of the 10-dimensional super Yang-Mills theory. But we can always rescale this coupling G Yang-Mills into these fields, so there is no tunable coupling in this model. Now, what are the symmetries of this model? So it has 16 supercharges, and it has an SUN gauge symmetry, which is a global symmetry, and the fields x mu and psi alpha, they rotate in this way. It has an SO10 rotational or Euclidean Lorentz symmetry. So we are interested in breaking of this Euclidean Lorentz rotational symmetry, spontaneous breaking of the symmetry. So dynamical compactification is realized via spontaneous symmetry breaking of this SO10 symmetry. So SO10 breaks into some small number which is less than 10, SOD times SO10 minus D. So some kind of breaking pattern is there. That is the question. Now, why do we need to apply complex Lanchovan method to IKKT matrix model? So we can look at the partition function. So exponentiate the action, and what we get is the Euclidean partition function of this model. So here, this is the action of the IKKT model, and what we can integrate over fermions. Since the fermions are real, so we have 16 real fermions. Once we integrate our fermions, what we get is a Pfaffian. So we can do this Beresin integral to get the Pfaffian of the fermion matrix M. And we can exponentiate the Pfaffian using a log, and we can rewrite the partition function as this exponential of minus S effective. Here S effective is the effective action which is obtained after integrating out the fermions. Now this fermion matrix, it is an antisymmetric matrix, and it is also a large matrix. It is 16 times n square minus 1 times 16 times n square minus 1. So when we take large n, this is going to be a huge matrix. So this matrix can be complex in general. So that is the crucial point. So the answer to the question why we apply complex Lanchovan method to IKKT matrix model. So this matrix can be complex in general. So it causes sign problem in Monte Carlo simulations. So as a side note, this is the same with the BFSS matrix model as well. It has a mild sign problem, which is dependent on the 't Hooft coupling in one dimension, and also the way in which the model is discretized on the lattice. So that can also cause sign problem. So we can write the Pfaffian in this way, take the phase factor outside, so separate out the phase, and we have the absolute value of the Pfaffian. Now, if the angle alpha is 0, we can do Monte Carlo simulations because the action is real. But for us, the angle alpha fluctuates wildly for models with SOD with the D large. So in our case, we are looking at SO10 model. So D is 10. So it fluctuates widely for that case. So Monte Carlo with phase quenched approximation. So that means we just remove the phase. So it has been performed, and there was no SSB, spontaneous symmetry breaking, in that model. Then bosonic IKKT was also explored using Monte Carlo and Lanchovan method. And there also it shows that there is no spontaneous symmetry breaking. So how the field is evolving in Lanchovan time. So we can update bosonic matrices in this way. So we have the effective action, take the gradient with respect to the field, x mu, and add a Hermitian Gaussian noise, which obeys those constraints I showed earlier. We can look at, so we can discretize this evolution equation, which gives us this. So here delta tau is the Lanchovan time step. So we can take this time step to be adaptive for much faster evolution and convergence. So here also we can encounter problems. So a priori we don't know whether the results are reliable or not, the complex Lanchovan results. So the problems we encounter are excursion problem. So that means the fields can wander off to infinity in imaginary direction. So we started with SUN fields, the XME matrices, but they can wander off to SL and C instead of SUN. So that is one problem. And the other is singular drift problem. Fermion eigenvalues, they can accumulate near 0. So that creates the problem in the evolution equation. So we need to control excursions into imaginary directions. So we can introduce something called gauge cooling. So for that, we need to introduce a quantity which is called Hermiticity norm, which is defined in this way. So it tracks the deviation of the matrix x mu from its Hermitian nature. So we notice something useful, which is observables and the drift. They are invariant under this transformation, where G belongs to SL and C. But the Hermiticity norm, which was introduced here, that is not invariant under this gauge transformation. So we can exploit this property to minimize the deviation from Hermiticity. So the gauge cooling process is something like this. So take the Hermitian field, or take the bosonic field, apply this gauge transformation with this alpha, which is a parameter, which can be a constant parameter or it can be adaptive depending on the situation. And this FA is given by this object. So we do this multiple times so that the Hermiticity norm, it decreases. It reaches a very small value. So we do that several times and we obtain another field x tilde mu, which is called the gauge cooled field. And we can use this gauge cooled field for the evolution of the scalar, the bosonic fields in this way. This is the Lange-1 evolution with the gauge cooling. So we can use adaptive gauge cooling, which leads to much faster evolution. So people have looked at this. Now the second problem is singular drift problem. So this happens when eigenvalues of the fermion operator, they accumulate close to 0. So here what we see is there is an M inverse of the fermion matrix. If the eigenvalues are close to 0, it is not easy to invert this matrix. So this is similar to what we encounter in lattice QCD, where there are difficulties with simulating at physical quark masses or physical pion mass. So the problem here is also similar to that. So what we do is we can avoid this problem by adding mass terms to fermions. So here we are looking at IKKT matrix model with a specific type of deformation. So we are adding mass terms to IKKT matrix model in a certain way so that supersymmetry is still preserved in the system. So this is known as polarized IKKT matrix model after this recent work from this year itself, 2025. But originally, the structure of these mass terms, it was introduced by this author in 2002, 22 years ago. So we can add this specific type of deformation to the IKKT matrix model, and this deformation is supersymmetric. The model, it doesn't break any supersymmetry. If we carefully look at these various terms, so here we have N3, which is added to the fermion as a fermion mass term. So it has this particular form. Then for the Gaussian part, x square, we have this particular form. And for the Myers term, where we encountered 3 fields, 3 x's, so we have this particular form. So here omega is a dimensionless parameter in this specific setup. So we have the IKKT matrix model, which has this particular action. And onto that, we are adding the supersymmetry preserving deformation. And the deformation terms are this. So here omega can be connected to a dimension full parameter mu, which has a dimension of mass through this rescaling. Now let's look at some simulation results. So we start with the bosonic IKKT model. So we remove the fermion terms. So what we get is this. So we have bosonic mass terms and a Myers term. So the full IKKT model with this particular supersymmetric deformation was explored recently, as I mentioned before, and 2 other papers came out recently after that. So they have looked at the gravity duals of this model at various deformation parameter regimes. Now, when the mass parameter omega is not equal to 0, the SO10 symmetry is explicitly broken. So it is broken to SO7 cross SO3. So that is very interesting. So there is only one unique supersymmetry preserving deformation of this model, and this model breaks the internal Lorentz symmetry in this particular way, which is very interesting. So for when omega equal to 0, we recover the original IKKT matrix model. So we can probe spontaneous symmetry breaking in IKKT model by first taking the large n limit, n goes to infinity, which is thermodynamic limit in quotes, because there is no thermodynamics here, and then the mass deformation going to 0 limit. Now, the mass terms, it is a blessing for us. It avoids the singular drift problem. So the fermion operator is modified in this way through this mass deformation term. So it shifts the eigenvalue distribution of fermion matrix away from 0. So that means this matrix has better condition number in our simulations. So here is a result from our simulations by looking at the eigenvalues of this fermion matrix. So here the mass parameter is set to 0. So we can see there are lots of eigenvalues close to 0, clustered around 0, which can be problematic in complex Langevin simulations because the simulations may not be valid. It may not obey the criteria I mentioned earlier. Now here are some other plots. So here we are increasing the mass deformation parameter, omega equal to 2, omega equal to 4, omega equal to 6, and we can see that the eigenvalues are being repelled from the origin. So they are shifting away from the origin, and we can increase omega further, 8, 10, 20. So they are being shifted further and further away from the origin. Now coming to observables, so we can look at this specific observable to track spontaneous symmetry breaking in the model. So this is called the radial extent of eigenvalues. So they are constructed from the scalars in this way. Take the square of the scalars, take the trace and normalize by n. So let's call this lambda mu. It depends on omega and n as well. So we will measure this quantity in our simulations. Now, the extent lambda, it has omega dependence. And for small omega, it goes like some 1 over omega power something. So that means it blows up for small omega values. So in order to remove that dependence on omega, what we do is we define a normalized extent defined in this way. Take the extents and divide that by the average of the 10 extents. And let's call this as rho. And this also depends on omega and n. So this ratio removes the omega dependence to a certain extent in the small omega limit. So the plan of action is, so we do simulations for omega not equal to 0 and then take the large n extrapolation. So then we must have SO7 cross SO3 symmetry breaking, which is explicit because of the mass term. After that, we can take omega going to 0 limit, which corresponds to the model we want, which is the IKKT matrix model. And we also monitor this lambda mu, and from this we can see if SO10 is spontaneously broken or not. So here are the simulation results from bosonic IKKT model. So we can ask the same question in bosonic IKKT matrix model. So here is the action of the bosonic IKKT model with this omega deformation. So this model exhibits no spontaneous symmetry breaking. So we can show this using Monte Carlo and also 1 over D expansion. So here are our simulation results. So this is for the bosonic model. So x-axis we have omega, various omega values, and this is for n equal to 8. On the right hand side we have n equal to 16. So for large omega, we clearly see that symmetry breaking pattern. So on the upper side, we have SO3 part. There are 3 eigenvalues or 3 extents, and down below we have 7 extents, which is much lower. As we reduce omega, something interesting is happening. So they are coming together and they are coalescing to form one single value, which is 0.1. So it's basically 1 by 10, which is 0.1. So we also observed some certain interesting patterns. So it goes up and comes back down, and it goes down and comes back up. So something strange is happening here. So this could be some kind of phase transition around omega equal to 7. So we are seeing the same pattern here as well. So the point is SO10 symmetry is restored in the bosonic IKKT matrix model as we take the mass, the deformation parameter going to 0 limit. So there is no spontaneous symmetry breaking in bosonic IKKT matrix model. So here is how the extents behave as we change n, as we increase n. So n is increased from right to left. So we can see that these eigenvalues are going down, their values, and they're trying to approach this limit 0.25 something. And this is the result obtained from analytical calculations from 1 over d expansion. So here d equal to 10 for us because there are 10 scalars, and this is the result coming from 1 over d expansion. So it is trying to approach that value in the larger limit. We can look at the bosonic action as well. So there is an analytical result coming from 1 over d expansion, which is d by 4 equal to 2.5. So in our simulations, the bosonic action is fluctuating around that value, around the analytical result. Now we can look at the full IKKT matrix model, or the polarized, the full IKKT matrix model with the omega deformation, which is called the polarized IKKT matrix model. So here we fixed omega equal to 5, and we looked at the symmetry breaking pattern. So here we can see the 7 eigenvalues are above the 3 eigenvalues. Okay, so it is kind of inverted. So what we expect is this should be above and this should be below. So here they are responding to large n as we increase n. So they are changing in a certain way. So here is another plot for fixed n equal to 6 and varying omega. So as we decrease omega, again, the symmetry breaking patterns are changing. So we can see there are some kind of breaking patterns happening here. But this thing is inverted, however, and we encountered some difficulties for omega below 2. So we are still looking at this. So the Lanchevin process was not converging. So we are looking into this for small mass. So clearly there is a breaking pattern. So now within SO7, we are seeing further breaking patterns, and within SO3, something is happening. So Hind said some SOD with d less than 7 breaking patterns. Now the question is, what happens at large omega? So if we increase omega further to the right, what is going to happen? So here is our preliminary simulation results for large omega. So we went up to some large omega value here. So what we are seeing is there is a phase transition. There is a sudden jump in the 3 eigenvalues corresponding to 3 directions. So here they started below the eigenvalues corresponding to 3 directions. I mean, the average over 3 directions compared to average over 7 directions, but around 110 or maybe 120. So we are seeing a sudden jump for n equal to 6 and n equal to 8. For n equal to 4, we are not seeing that jump, but it may jump after if we increase omega further. So there is clearly an n dependence in this jump, where this jump is happening. We can look at the unnormalized extent as well. So here also we are seeing a similar pattern where the eigenvalues corresponding to 3 directions, they are suddenly jumping around omega 110, 120. So if you look at the bosonic action, normalized the various components of the bosonic action normalized by the full bosonic action, this is also showing a jump around some value of omega, around 110. There is a significant increase in the Myers contribution in the system. So this is in agreement with this paper by Hartnell and Liu, the recent paper. But for us, large omega is omega around 110, 120, where such a transition is happening. So with that, let me show another plot, which is the radii R3 and R7. So we can see that transition here as well. So R3 is jumping around this value. So this could be suggestive of the fact that it is going into the Myers vacuum in the system as we increase omega. Okay, so let me move on to my final comments. Complex Lanchevin, it is a useful tool to study models with complex actions. So we looked at some simple examples, supersymmetric quantum mechanics, and we looked at a very interesting example, which is the aggregative matrix model. Bosonic aggregative matrix model, it has no spontaneous symmetry breaking in the large N limit. So it supports the claim that the Pfaffian, it plays a crucial role in spontaneous symmetry breaking. So we find the presence of spontaneous symmetry breaking in full aggregative matrix model, but we need larger N simulations to get more insight into this. So large N simulations are still ongoing. So with that, let me end my presentation. Thank you.
So I would like to speak about what I would call BFSS to quantum gravity. My talk will really consist in several observations brought together, hopefully, in coherent synthesis. I will first introduce the matrix harmonic oscillator, or the BFSS2 harmonic oscillator, and quantize the system. And I will find that I get several non-commutative geometry spaces. In second step, I will try to quantize that non-common geometry. So the first step is really first quantization. The second step is second quantization through matrix models. I will focus on the concentrate on the Euclidean spaces, but also there are Lorentzian ones. Then I will introduce emergent gravity and ADS to black holes. It is an extension. In this last part, I will introduce a generalization of the matrix harmonic oscillator. It's an OD matrix harmonic oscillator, and try to argue my way towards recovering the emergent geometry. So that's what I call latent geometry. It's the emergence of the emergent geometry that has been lost in the Young-Mills phase. If I have time, I will discuss the generalization to the actual BFSS2 quantum mechanics, and then I conclude with a summary. So the basic model is really simple. I take one matrix model, so I have the degrees of freedom is an n by n Hermitian matrix X, and of course I will also introduce a momentum matrix P. And I write so this will contain the trace part and the traces part. Then I write simply a Lagrangian for harmonic oscillator. It's already gauge fixed there, but just to argue that the difference between the ordinary harmonic oscillator and the matrix harmonic oscillator is the requirement of gauge invariance, which you can see by the existence of the trace. If you want the Lagrangian to be invariant under SUN, then we need minimal confidence and introduce introduction to gauge field in the usual way. So this is the model. It's given by the action in the last equation, where lambda is a math. I take it to be squared. This is in Minkowski signature. So this is actually the bosonic part of the maximally supersymmetric mass deformed BFSS2 matrix quantum mechanics, which is a simplified version of the original BFSS or BMN models. So it includes just one matrix. So I quantize them. Quantization clearly means gauge fixing, means going through the constraint analysis and everything. This is a really simple system, but not that simple. So you go through it, you recover the Hamiltonian and the correct Dirac brackets, which you quantize, you get your commutation relations. Now, the main result now is that these commutation relations will hide actually, I will reconstruct it now, but is actually the commutation relations for the trace part. If I just take the trace part, do you want trace part, trace sector? So this will correspond to the ordinary Heisenberg algebra, ordinary matrix harmonic, ordinary harmonic oscillator, which is your non-commutative plane. The SUN sector will realize two spaces, the pseudosphere, the hyperbolic plane, and also the theta space. One of them is Euclidean, the other is a Lorentzian. The other two spaces can only be obtained within this scheme, can only be obtained via rotation. If you go back to the supersymmetric completion of the matrix harmonic oscillator, we get the supersymmetric spaces corresponding to these non-conjoint. So let me go through this derivation quickly. So first of all, we construct our observable, our quadratic operators. The first one is the Hamiltonian, which I do not by K0. Then there are two more, which will really play the role of dilatation operator and conformal transformation generator. So this is the three generators of this constructed from SUN traceless matrices. And they, after some calculation, we discovered that they form an F12 Lie algebra. And I compare just for pedagogy reason, I compare with the S03 Lie algebra. So this is my basic structure. It's an S1 to Lie algebra, which actually generates the Lorentz group in 3 dimensions with metric 1, 2. It is also actually the conformal algebra in 2 dimensions. So I construct now the representation theory. I start with the Casimir. As you can see, it has signature -1 + 1 + 1. Okay, they were going in some direction. And then I construct the Bergman reducible representations. I construct the Hilbert space explicitly and I compute it. The solution is given by Bergman. And we have 3 main reducible representations. The first and the second are what interests us. The first is the discrete series, which really behaves more or less like so it has a pseudo-spin quantum number K, which is integer or half integer. It's very similar to the SO3 spin representations. The second one is the continuous series, in which the pseudo-spin is actually a complex number. So the most important observation here, which will allow me to write down the non-continuous spaces directly, is that in the discrete series, the Casimir is negative. That will select the pseudosphere and also the onto d theta. Whereas in the continuous series, the Casimir is actually positive, and that gives me the d theta space. So these are the solutions. I write them out just for completeness. I write the commutation relations, the embedding relation, the Casimir and its relation to the radius and also the deformation parameter. And after substituting the solution, I get the quantization condition, and that tells me everything. So the minus sign will correspond to so the positive Casimir will correspond to a continuous series, which is d theta. That is a d theta metric. Whereas the negative Casimir will correspond to discrete series, which is the hyperbolic plane or the pseudosphere. So these are the main solutions I have. The commutative limit is clearly obvious from the quantization condition. You take the kappa to 0 or the the representation number, pseudosphere representation number to infinity. You recover the Poisson bracket on either the sphere or the pseudosphere or the theta space.
Excuse me, is this the solution to the classical equation in motion?
Which classical equation of
What
motion?
do you mean by classical solution?
I did not say classical solution. I meant classical limit. Classical limit in which this space will approach this commutator will approach the Poisson bracket of the symplectic manifold. So we have here the S2 and H2. So we know the symplectic structure there. That commutator approaches that structure in the limit kappa goes to 0 or k goes to infinity. I'm talking about commutative limit.
X0 is the gauge field.
X0 is here in this construction. X0 is actually the energy generator of time translations, and X1 is the one associated with dilatation. X2 is the one associated with the special conformal transformations.
Oh, I see.
This is at the level of this BFSS2 harmonic oscillator. There is no matrix boundary yet. The quantized, what I have shown here is that the quantized phase space of that system is given by these symplectic manifolds. And I get the pseudosphere and the theta directly. The other one, they are obtained by weak rotation. So these are the four spaces I obtained. Of course, remember that we got also the Moira plane in the traceless in the trace sector. So this is just to show you how to do Wilk rotation here clearly, so that what are the relevant representation you get. I will just skip this part. Now, what we have really done here is that first quantization, we quantize some symplectic structure to obtain some non-convex geometry. I'd like to do the second quantization, which is that to write those solutions to write those spaces as solutions, classical solution of some matrix model and define a path integral. That's the second step. So clearly, I would like to work with Euclidean signature, but you can also do this for Lorentzian signature. Formally, you can do it, no problem. So the model, this model is actually a generalization of the is a D equal 3 Young-Mills matrix model. It's a D equal 3 with 3 matrices. It's a D equal 3 Young-Mills matrix model. So it's an IKKT-like model in D equal 3 dimensions, and it contains also a Myers effect term, which is the Chern-Simon term, which is the one responsible really for the condensation of the geometry. And here I write the complete action, which for certain values of the parameter alpha and beta is a complete square, but not necessarily a complete square in general. So I get this model. I will not go through the derivation. I think everybody knows this. And just here, comment on the quantization, the sphere. So what I have done here in writing these matrix models, actually I have Wilk rotated this theta space. I have Wilk rotated this theta space to the sphere. I could have written the matrix model for this theta space, but let's just not do that. I mean, let's just stick to Euclidean signature as much as we could. So this matrix model really is relevant for the sphere and the pseudosphere. That's what I want to say. The sphere is finite dimensional, so you can do quantization in an obvious way. The pseudosphere, really the trait is infinite dimensional because the discrete series is infinite dimensional, but it admits a natural regularization. You just cut the trait at some point. The pseudo spin quantum number really looks like a spin. That's why I chose to work with Euclidean signature. So that's what I have. So I just a word on regularization, and then we just quantize and we compute the effective action. And our parameters are this alpha and this tau, the ones I was writing in the model. So the Chern-Simon and the mass term. And so I just find out that there is a transition. That's a well-known transition. So as we decrease tau for fixed values of alpha tilde, so we need to scale alpha up, we get the system undergoes a phase transition from a Young-Mills matrix phase, which corresponds to some order parameter equals 0, which is essentially the extent of space, to a non-convex geometric phase characterized by phi different than 0, which is the extent of space has condenses to some non-zero value. That's actually the sphere or the pseudosphere. This is the so-called famous emergent geometry phase transition. So the geometry really emerges only as the system cools down. Here, the temperature, the magic temperature is really formal temperature, is the inverse of the gauge coupling constant. The order parameter can be taken in various ways. Here I choose the Chern-Simon term, and it is different than 0 in the geometric phase, and it is 0 in the Young-Mills phase. This is an actual this is an actual phase there for the phasosphere matrix model in that parameter space. So this is the basic idea I have. We have performed first quantization as second quantization. Now, I would like to extend this to emergent gravity and non-convex black hole. And the basic idea is that the matrix harmonic oscillator realizes a non-commutative ADS2 phase space that we have seen. So which has symmetries matching the symmetries of the conformal mechanics of the DIAS on the boundary of ADS2. So that's the idea. The basic idea is that we have a non-commutative ADS2, which shares the same boundary as the commutative ADS2. On that boundary, what we have is the magic harmonic oscillator. That's one way of looking at it. Or you have the so-called DIAS conformal quantum mechanics. So that's the basic idea. So we know how to extend that solution, the commutative ADS2, into black hole. That is using bulk dilaton gravity. As we know that. So the role that will be played by the dilaton gravity here is an IKKT-like model. That's the punchline. They would like me to show this idea. So here I'm trying. Here first, I would like to show you that the conformal algebra. Here I'm going to show that the conformal algebra really matches that of boundary ADS2. So we start with our matrix operator X with scaling dimension delta. So the conformal transformation is written in this way. So we can find that there are three independent solutions, and they correspond precisely to the generators of S12 with the correct algebra, and I can write them explicitly. I can solve and find exactly the differential form, and you can see that they are different from the usual form just by the dependence on the function f. So I know now directly from this form that the diffeomorphism needed to map it to the correct to the conformal quantum mechanics is T goes to capital T equal Ft, where F is the generator of conformal transformation, and that will give me precisely the algebra of the AFF quantum mechanics. The Hamiltonian is given in equation 7. So the point is, what we have this, the algebra matches. Second, the commutative and non-commutative boundaries match. Asymptotically, ADS2 is actually ADS2, then there is no difference. And therefore, the bulk dynamics, which is dilaton gravity in IKKT, is conjectured to be generated or is equivalent to an AKKT-like construction in the matrix model, and that's what we are going to do. So here I just write down the ADS-T black hole, the one known from dilaton gravity. I have the Tekel-Barron action. V is quadratic potential. I write also the embedding coordinates in terms of the embedding coordinates, which will become operators. I write them here in local form, in local coordinates. And I write also the ADS2 spacetime without dilaton.
Sorry, can I ask a question? What was the theta parameter in your H theory or harmonic oscillator system?
There is no theta parameter, it's quantization. So, I mean, the theta parameter isn't the commutative, essentially. It's each bar. It's just each bar, essentially. It's just when you quantize, there will be an each bar, and there is a scale, and that's what we call it theta. Here I call it kappa.
So when you said this was equal both to ADS theta and a classical, you meant that the theta goes to 0?
No, I did not mean that. What I meant is that the ADS2, you can think of it this way. So this is your ADS2. Let's theta. So it has some non-common cell structure. It's space-based, quantized space-based. But as we approach the boundary, it's really the boundary of an ordinary ADS that you can show using star product statistics. So in some sense, you can draw it this way, that here, ADS2, theta, this is its boundary. It is the same boundary as an ADS2. I'm not taking limit here. So it is, so this structure, this non-common structure is only in the bulk. And I know that in the bulk here, I have a dilaton. Here, I would like to reproduce it using an IKTT or something else. A non-commutative, not necessarily an IKKT. I will here pursue the IKKT, but there is a better way to do it, actually. I will also talk about it.
This whole bulk and bound.
Yeah, so ADS2 here you have DIAS. What is it? Sorry, this is ADS. Yeah. ADS2 commutative is dual to DIFS. That's the actual contractor, but it's correct from the perspective. I'm claiming that the ADS2 theta here is DFS. And they share the same algebra. They are on the same boundary. And this goes to this, the commutative limit. So that's why I am going to take the solution for this space.
What was DIAS again?
This is conformal quantum mechanics. The usual solution due to Del Faro and this is the Hamiltonian. I don't recall the name, so I cannot recall it. So this is the Hamiltonian, just ordinary quantum conformal quantum mechanics with the F12 symmetry. So this is here. So the black hole. So this one will be extended to an ADS2 black hole because of this set of consideration. That's the idea. And I will start with this black hole and try to quantize it. That's what I'm trying to do. So I start with the ADS2 black hole. This is the formulas. So the actual dilaton is 5. And as you can see, the actual black hole depends on the parameter A, which determines the mass, the horizon, and temperature, and everything. You can think about this A as an acceleration, going from ADS0 to ADS plus, where ADS0 will play the role of ADS0 will play the role of Minkowski space-time, whereas ADS plus will play the role of Rindler wedge. So here, the Hawking evaporation process is really an architect. That's what I'm saying. But never mind that. I have now this structure. I'm going to quantize it to write the non-commutative ADS black hole. So the basic observations are rather simple. I take the dilaton and express it in terms of the coordinate, global coordinate. I find this formula. Then I simply quantize by introducing Hilbert space. So x hat 1 is now the matrix coordinate of ADS2, and phi hat is the dilaton field, which should be given by this constraint. And I can check that it satisfies this set of commutation relations. More importantly, remark that this set of commutation relations are not S12 invariant, but there is a formulation for the sigma model of this. I just write it directly in the non-commutative setting. That's the constraint number, the equation number 10. Phi is the dilaton field. Ka are the generator translation on ADS2. This will go to this equation in the commutative limit, which is known as the solution of ADS2 black hole in the commutative Jacquier theta bound map. So it has the correct commutative limit and everything. So how can we then? So the correct way really to introduce a black hole here is as a scalar field. Scalar field on the ADS2 background. So we have an ADS2, a non-commutative ADS2 background, and I have on it a scalar field, which is given by this constraint. So the phase transition between a dilaton and a no dilaton phases is really given by the phase transitions of this scalar field in that geometry. That's really the correct way of doing it. But I'm not going to do this. I'm going to pursue another direction.
So you're saying this is like a quadratic Casimir?
It plays the role of the quadratic Casimir, exactly.
Yeah.
The quadratic Casimir are, yes, it plays that role. It plays that role for the dilaton. And it is fully invariant everything. So it's very nice. You have a very nice scalar field theory if you want to do it this way. The other way is that to promote the dilaton field, to promote it to a gauge field, so there will be a fourth coordinate, matrix coordinate, x3. So x3 is phi hat, and I write the curvature tensor, the usual way, where so the second line is the non-commutative ADS2, the one we had in the first quantization. The first line is actually the dilatonic fundamental commutation relations. You put them together, you get this one, and then you write your gauge transformations, you enhance your you extend your theory to U and gauge theory, and you write your perfect square action, everything. And then you drop the terms that you don't need really to get this action, which is fully SO1 to invariant, SO1 to invariant, and it discards non-commutative ADS2 as the classical background. This is nice. So it has two parameters. First is alpha, which is a Chern-Simon term, Chern-Simon coupling, and second is alpha 1, which is essentially the temperature. So this is the model that I would like to discuss. The first transition is exactly like before, essentially. I mean, we have here we just have two terms. We have two Chern terms. The first one really condenses the geometry. The second one condenses the dilaton field, and they are in competition. So you could have one or the other, you could have both. So the structure will look like this. So you have, so as I said, the first one is emergent geometry. The second one is condensation of the dilaton, which is emergent gravity. And the Hawking process here, which is the Anosh process really, the one I was speaking about, is actually a phase transition from Yang-Mills matrix model to from the Yang-Mills matrix model. Sorry, the Hawking process in the Yang-Mills matrix model presents itself here as a transition from a gravitational phase to a geometric phase where the dilaton has a non-zero expectation value to a phase where the dilaton is actually zero. That's a nice, and it's fully, all the models I'm putting down here are actually unitary. So this is an evaporation process which is completely unitary. There is no, so that's the idea. So this is the basic structure. We have three phases: a gravitation phase in which the dilaton, the coordinate condenses around x hat a, and the dilaton condenses around d1, and we have a geometric phase in which the dilaton goes to zero. Now it fluctuates around zero. And the third phase, which is the Yang-Mills phase. So this is the structure I obtained from this. So these are the ADS to black hole, and this is the emergent gravity in this context with evaporation process, which is completely unitary. So this is the main part of the talk. The second part is really has some really. So what I'm going to do is to generalize the matrix harmonic oscillator to an SOD model, SOD matrix harmonic oscillator. And so what I'm going to do is to do that. And so what I'm going to say is that in the high T, large D, or instead of saying those things, I'm simply do that and see how can I say that. So let's generalize. What can we do? First of all, we can add polynomials. That's very interesting. That's one generalization. We can also add more matrices, and that's the line I will follow. So this is the line I will follow, and I will take more than, and I do more than that. I will take actually the large D limit of this. So I have simply the Yang-Mills matrix model, Yang-Mills quantum mechanics, just this model, and I take the large D limit, and there are very nice results. The references are in there. Very nice results. So they show that this model, the Yang-Mills term can be approximated by the mass term, this mass term, where the value of the mass is essentially given by the dimension cubed. That's a very nice one. And this results hold for any number of matrices. As long as D is large, you get this. So what I'm proposing is that this is my starting point, actually. This is the OD matrix harmonic oscillator I would like to start with. You can quantize it, and you find usual way, like we did in the first case. And the main obstacle you get is the Gauss constraint, which does not diagonalize. So that's, but if I can assume in some sense that the matrices are mutually commutative, then the whole system diagonalizes, and the BFSS D plus one, the BFSS D plus one harmonic oscillator decomposes into BFSS 2 to the power of D harmonic oscillators. So that's the idea. I like to give some arguments. The first one is that, let's take, for example, the Euclidean matrix harmonic oscillator. Take the original model, and I take this original model I was writing down. This one in Euclidean signature. Yes. And then I take this one, and then I take dimensional reduction of this one, 2 points. So that's my, it's not an IKKT, it's an IKKT2 like model, because you look at the commutator, only commutator of A with the x's appears. There are no commutators between x1, x2, or things like that. It is an IKK2 like structure. It's a Ydri model. Now, this is second step is that I'm going to quantize using the background field method, and there is a long held belief that this kind of models are one loop dominant. So I just do one loop and I compute, and then I integrate. So I get an effective action with respect to the gauge field. Here I have to say from the beginning, I did not say that I gauge fix by adding a mass from the beginning. So the gauge field appears with the mass capital F, and I follow this logic. And then I solve the model at the end by a saddle point, and I get this result, which can be expressed as the partition function of the BFSS2 model to the power of t. So at least at the level of the partition function, the OD harmonic oscillator decomposes into copies of the single matrix harmonic oscillator. This can also be seen actually from the Molian wire formula. You can actually do the integral explicitly. Denjus and Sanjay did that. So you can do the integral and you find your results. I write here the bosonic, just the bosonic sectors. And these are the results. The delta is the Vandermonde coming from the gauge fixing, from the gauge. Delta gauge is the Vandermonde coming from the gauge fixing. And delta boson is the one that is coming from the matrix, the coordinates. And the difference is only in D. So this is the result. Now take the large D limit. You can see also that there is the decoupling that I was speaking about. That Zn of D plus 1 is essentially Zn to the power of D. Here, what I'm using the fact that in the high temperature limit, of the BFSS, the distribution is actually the Gabor distribution actually approaches a delta function. So thetas will be accumulated at one point, and they will approach that point like 1 over beta, like 1 over t. So this allows me to do this calculation. So I know that at this level also it looks good, but so this is the idea here. So I'm going to assume this. So for the rest of the talk, that
Sorry, can I ask, what was the evidence that the interaction with the different matrices became irrelevant, or how do you decouple them? Because you started the model 2 pages ago, where you had interactions XA and XB.
here
Yeah.
I start with this one.
So what's the evidence that?
That is a large D expansion. Large D expansion, you solve the saddle point in the large D expansion, and you get that this dominant saddle coming from this young mill is actually given by this quadratic.
What is 11 and 12? Or who showed this?
Mandel and Mandels and Comban. Yeah, Mandel and Comban.
You can interpret it in the following way. We have a lot of matrices, each one of them becomes random. When you do commutators with completely random matrices, enough of them, they average to something constant. And it's kind of like this kind of a master field things where it's going to be SOD invariant and other things. Because there's so many of them, they self-average. You forget about the fluctuations of the other ones. And you get the simple matrix model. But this is kind of statistics of very large of some kind of master field.
Yeah.
It's kind of like going like mean field.
Not mean field, but.
Yeah.
Numerical evidence?
What's that?
Yes, some numerical evidence.
Yeah, I'm going to say some numerical. Of course, there is some. That's there. So here. Now, here what I'm doing, I'm going to compactify. So before I do that, well, I should do that. So I'm going now to compactify the meshes model I had before. The ones I was writing, they are IKKT3. I convert them into BFSS3 quantum mechanics. That's the idea. And D with D equal 3. So really here, large D for me is I really am dealing only with D equal 3. So D equal 3 is sufficiently large for this sort. So like all the SQCD when they say the color is 3 is large. But just for the sake of argument, just bear with me. So so that's the idea. So first of all, this is the first observation. The second observation is that the high temperature limit, the Euclidean BFSSD, therefore, D plus 1, therefore, in the infinite temperature limit, will go to the IKKT D plus 1 model in the Yang-Mills phase. And the dominant dynamics there is given by commuting meshes, actually, but not any commuting meshes. So these commuting meshes are actually distributed according to the, I'm going to say this here, that you just say it then. These are given actually by the so-called uniform Bohr distribution. So they are commuting matrices with this distribution in every dimension, and that's the numerical. So this is the so if D is very large, so if D is very large, we can say that the BFSS D plus 1 will go to harmonic oscillator, but then the harmonic oscillator will go to the Wigner law. That's not correct. What you should do really is that you compactify first, you get IKKTD plus 1, and then you compute the eigenvalue distribution. It is given by this uniform Bohr distribution, which is saying that the matrices are distributed uniformly inside the ball. So this is the idea, and that's one thing. Now we have this model, the BFSS3, and we have now a large D expansion of that, and we would like to say something. So if so, both, by the way, both the sphere and the pseudosphere matrix model will go to the same BFSS3 in Euclidean, which is given by this, and just the normal act. So the main observations. First of all, dimension reduction of BFSS3, as I just mentioned, describes both the sphere and the pseudosphere in the Yang-Mills space, where the dynamic is dominated by commuting matrices. Second of all, then I assume that we can use the BFSS matrix harmonic oscillator. So I can replace with this BFSS with the matrix harmonic oscillator. That is a quadratic potential. Third, I'll assume, well, that means if that is true, then large D and high D, the BFSS D plus 1 decompose in the direct sums of BFSS2. And we have, for D equal 2, we have two copies of the BFSS2 space in that case, and which is the reminiscence of the 2-point space of cones. But remember that the BFSS2 quantized gives you ADS2, gives you sphere and pseudosphere. So we know this. It gives you ADS, the theta and pseudosphere. So what we have now is that in the high T, in the high T regime of BFSS3, the model really describes direct sum of two de Sitter space or direct sum of two pseudospheres. And that's the main result. So the first case, what we have really, we started with the BFSS2. We started with the BFSS2 quantum mechanics. We obtained this object, the theta space. We weak rotated, we obtained the sphere, then which is described by AKKT3. Then that is in the geometric phase. Then that one in the Young-Will phase was replaced by BFSS3, which is equivalent to these two spaces. So we have here something like emergent time. We have a sphere, a Euclidean sphere, which goes to direct sum of two de Sitter spaces. So we have really here the weak rotation which we had performed really is undone here through this dynamic. Or the second case is that I go from the which is relevant to the pseudosphere. Same thing. We have a pseudosphere. We have the FSS2 quantum mechanics. We have a pseudosphere. We describe by some IKKT. Then it goes to two copies of the pseudosphere through the BFSS3 description in the Young-Mills phase. And that's what I call emergent time and latent geometry. Because geometry, the idea here I'm trying to convey is that the geometry that has emerged really is not gone. It's there. You have only to re-encode it in a different way. And that's really the main message. I mean, these emergent geometries really are transformed geometries. They're not really emergent in the sense that they are completely lost in the Young-Mills phase. That's really the main message I want to convey. And this is my generalization, which I will skip. And then I go to the summary. So what we have here is that first quantization gives me DS2. DS2 needs to be rotated to get an Euclidean answer. Second quantization, that's an emergent geometry. I get some IKKT or IKKT3 or IKKT4 for black holes. Then I compactify and take large D, which allows me to obtain the BFSS D+1 harmonic oscillator. A third quantization, which I call third quantization, is to try to recover that geometry again, but I get copies of, not a single one. But the original model with Euclidean, I can only get it again with the Lorentzian signature, and that's what I call emergent time. And also the hyperbolic plane of the pseudosphere, I simply recover two copies of it, and that's the main result or main observation. Thank you very much for patience.
Right, thank you. And I have something sort of follows up from yesterday's discussion, but I want to be a bit more precise in certain aspects of the extended symmetry that arises from celestial holography. And in particular, I'm going to focus. So yesterday I mentioned these three topics, and I will focus today on WN, which is something I mostly learned from Jan's paper. In the WN as a large n limit of SUN. Right, so this was way before the large n limits were considered to be holographic, but we will see that this has some interesting connection to celestial holography. And let me just start. Well, I will also briefly tangentially mention the connection to a fuzzy sphere, and hopefully the connection to some dynamical symmetry. If someone asks the right question, then I can go on and talk about this, explain how Laplace-Runge lens vectors show up massively when you have self-dual structures, essentially because you have hyperkähler space-time, and hyperkähler space-times do have Killing-Yano tensors and so on. But if someone asks in that direction, then I can go on an extra hour for all this. But let's just take for now. We will stick to this discussion. So let me explain first why this discussion is interesting. The discussion of WN as a symmetry of certain theories. WN famously is not algebra that's linearly realized in the same sense as beta pseudo algebra can have primaries, and there is some commutation relations. The argument is a bit more special, but it does simplify when n goes to infinity, in which case it becomes a linearly realized algebra. Okay, so yesterday I did a little sketch on what my picture of physics is. Essentially, it starts with an 11-dimensional ultraviolet finite theory of quantum gravity. Okay, so that could be M theory. And then in our work, we measure this 4D effective field theory observables. And we measure observables in the same sense as we cut off some energy in our detector, and we can see what particles we're probing at those energies. So obviously, there's an energy level here that doesn't quite probe quantum gravity. Those energies are very small. So we abstain from creating black holes and more exotic states. Essentially, by the time that you create a black hole, your detector is absorbing the black hole, so you don't really care. I want to introduce, so yesterday I mentioned this, but actually I end up talking about something called the self-dual gravity, and there were plus helicity sectors and all that. So this is a bit of a cheating, right? Because I'm not interested, for this talk, I'm not interested in this plus and minus sector of gravity, but I'm only interested in the plus sector. So in the sector where most of my gravitons have plus helicity, I define that to be self-dual sector of gravity. And I said, okay, if you start with states that are BPS or half BPS, eventually you will see self-dual things. But there is a more intrinsic way, if you are a mathematician, to define what the self-dual sector is, and that's where all these factors come in. And I'm gonna go on a limb and define it as a compactification of a particular UV theory, which is UV finite, which is a twistor theory. Okay, and this theory lives on a CP3 form. But because I don't like supersymmetry too much, I actually will just think of it as a CP3 theory. So it's in particular, it's a 6-dimensional theory that doesn't live in the space-time. It's compactified by inserting some defects. So there's D-branes here, just like in this case, there's M-branes. And so these D-branes actually, and there is a D-brane that essentially reduce the theory to the self-dual sector. The theory itself has some complaints. So if you actually look at twistor space, everything is conformal invariant in a higher sense. So the symmetries of CP3 are SU4, and SU4 is essentially a version of SO6 or SO4,2. And so this SO4,2 is some higher version of the conformal group in the, so it's essentially a conformal group of Minkowski spacetime. But so the theory has some extra structure, and in fact, you can check that the theory is either finite, just because there is a notion of this conformal symmetry that prevents the IR divergence. But nevertheless, we can do calculations in this theory, and we can obtain final answers, and then we compare that answer to the 4D full answer in the self-dual limit. Okay, so if we look at certain sector of this theory, then we can match that to year. Okay, so I keep talking about self-dual symmetry, so let me just write some actions so that we can all be in the same page. So the action of self-dual gravity has it's sometimes people refer to as BF action. What it means is that it has a Lagrange multiplier, and it has so it's a 4-dimensional action. I could just write a Lagrangian here, and then it has a qubit interaction. So h is just a number, okay? H is just a function, and you can think of h as being the plus helicity graviton, which is sort of dynamical, and h tilde as being the negative helicity graviton, which has been integrated out. So now it's just a Lagrange multiplier. So you can solve the h bar dynamics is trivial, or it's a free field in a sense. And let me just define what this means. So this is a Poisson bracket here, but I'm defining it in the spacetime. So what it means is that you take two coordinates. So for all of you who are familiar with the light cone gauge, this is essentially a Poisson bracket defined in the light cone gauge. So it has two coordinates. Let me just say u is something like t plus sif, and w is like x plus I y, and then just compute the Poisson bracket in those coordinates. Okay, so it's a particular direction of the momentum on the light cone. This happens to match if you were to compute amplitudes in this background, the amplitudes are 0. If you can see this by checking the interaction term, if you try to compute amplitudes with 1h, so if I try to compute amplitude that only has h, or Feynman diagram that only has h, I find that I really need an h bar to run. So if I only so if I only have external h's, then the amplitude is 0 at tree level, and that's a reflection of integrability. Okay, so this amplitude vanishes because the theory has infinitely many conserved charges, and that's actually
some indices presumably, so that some bracket of h for h.
There are no. Oh, sorry.
Yeah, but then why isn't it the same?
Right, sorry.
Yeah.
Thank you so much. Yes. Yes. So okay. The amplitude vanishes as I mentioned.
What did you write inside the bracket?
Yeah. So Andy pointed out that in fact, if I just write it in
Yeah.
so because gravity is cubic, and the curvature tensor is quadratic in the curvature, then there has to be two derivatives. So the Poisson bracket gives you one, and then you have to put another derivative. Yeah, sorry.
So is this the theorem you're claiming is UV finite?
Yeah, this theorem is UV finite, and it's IR finite because in fact, the amplitude, if you were to compute the amplitude, the only non-trivial amplitude is it's one loop exact. And it comes from the fact that h, there's an h bar running in the loop, and so that's the only sort of Feynman diagram in this theory. And it's
sorry, h is a function of u with w.
H is a field. Sorry, this is a 4D Lagrangian. Yeah. So h is a field. It just happens to be non-Lorentz covariant. Okay, so this is something that simplifies the formulation, but it obscures the Lorentz symmetry. So you should think of this as a light connection.
And you said something about h bar. H bar is
a Lagrange multiplier, which is reminiscent. If you were to derive this action from the full year action, you would have to integrate out h bar and discard the interaction of h bar. So this is usually done if you have a Chern-Simons term, sorry, a Euler characteristic term. You can sort of map this to the subswell action if you discard some coupling. But yeah, so it's what's left of the minus helicity diagram. Okay.
And is it t plus iz? Is it complex? T plus. Is it t plus?
Correct. Yeah, this is complex.
T plus iz.
No, U is a light cone. It's a usual.
U is a normal light cone.
Yeah, it's a usual advanced or data time, and W is
it's a complex.
Yeah. Okay, great. So that's the self-load action, and in fact, as I mentioned, it's integrable. The amplitude is vanished, except for this amplitude, and the amplitude itself can be considered as an anomaly, but let's not go into that. But most of the amplitudes that you can compute vanish. So that's a imprint of that W plus 1 plus infinity symmetry, which I should mention acts in this plane as simple generators. So if I take a function that depends only on U and W, so this is my function, PU and PW. This is one generator of symplectomorphism through the Poisson bracket. And if we compute the algebra structure of these generators, we find that obviously it's a symplectomorphism on the plane, and that actually goes to W infinity algebra. But there is a more interesting case that you can study once you accept that self-dual theories exist, at least in this sense, which is the non-commutative version of this. So this is what connects to Wn. So in the spirit of what Jens was asking this morning, whether we can compute commutators, we can actually write down Lagrangians with commutators that are non-commutative. That sounds a bit weird, but let's just say that we can replace this commutator by an actual, this Poisson bracket by an actual commutator, where instead of taking a normal product, I just take a star product. Okay, and that goes by the name of Moyal bracket. I replace this by my Moyal bracket, and then that becomes what people call the Moyal deformed self-dual gravity. Okay, I should explain. So when I replace this by Moyal bracket, what I'm essentially doing is that I am taking this Poisson bracket and I am exponentiating the Poisson bracket in a way. So let me write that more precisely. So I mentioned there is a commutator between this F, so F of P1 and F of P2. If you were to compute the commutator, it looks like, oh, can you still see this? Yeah. So it looks like P1U, P2W minus P1W, P2U, F of P1 plus P2. Okay, so essentially this is the structure of the Poisson bracket. If I am to compute the Moyal bracket, instead of having this structure, I find that it becomes the sign of so I have to introduce a deformation parameter. Usually that's called H bar. I'm just going to call it alpha. And here I write the same thing. Okay. So this is anti-symmetric. It satisfies the Jacobi relation and all the properties of a bracket. So this is essentially a deformation of the usual Poisson bracket that you sometimes call the deformation quantization of the classical symmetry. But in this case, I mean, you close your eyes, you can compute the solutions of this Lagrangian with that bracket, and you find that there are certain solutions which look like non-commutative instants. So, for instance, solutions of the self-dual sector. I mentioned yesterday that we have the tau-NAT solution. In the Euclidean slice, that is an instanton. And that's a solution, it's an exact solution of the self-dual gravity. If you were to promote the self-dual gravity to the Moyal deformation, that would be presumably, although I'm not entirely sure, because people seem to disagree on some properties, there will be a formation of this symplecton that looks like a non-commutative. Okay, so
Sorry, alpha is the deformation parameter, and then
Yeah.
you divide by alpha and take the limit.
oh yeah, sorry, there is like at some point there was a 1 over alpha.
Yeah.
Okay, so I'm sure most of you have seen something like this before. I'm not going to explain it further. What I will do is, for now, I will try to connect this. So this story has been known, I guess, for some time, and people like Penrose famously introduced this nonlinear graviton construction and self-12 construction. But I will now connect this story to what I showed you yesterday, which is actually why or how we ran into these structures from scattering amplitudes in 4 dimensions. Okay, so let me just go back to where I left yesterday. Okay, so yesterday we were looking at this amplitude, which has most of the class gravitons except for 2. And then there was a sub-theorem which appears when we take the residue of some of these states where the weight becomes 1 minus n, when n is a natural number. And the result can be written as a power of the angular momentum operator to some power, let's say n. And this angular momentum operator acts on particle I. So if you were to write it sort of explicitly, it would be something that looks like this set I. So this would be just to say the L0 component acting on particle I. And then there would be the L-1 and the L1. This is usual representation of the conformal group. And now the amplitude will have 1 less particle. Okay, they start from 2, and so on. It has 2 maps. One thing that I didn't write down because I sort of sketched the formula is that this actually involves a pole, and the pole has to do with the location, the way this formula remembers the location of the particle that has been taken to itself. So if I call that location Z1, the pole of this formula, yes, in agreement with the usual expectation from CFT, it's a pole that locates at one of the locations of the extra particles. So here in particular, I'm summing over all the other particles. But you can see that when I take Z1 to be very close to Zi, then I get this structure, which is the collinear limit applied to my extra particle. Okay, so this is a statement of the amplitude. So you can compute this statement from just 4-dimensional gravity amplitude. But more importantly, it has simple pole, which is very suggestive of the OP. And in fact, the interpretation that I proposed yesterday is to think of this as an SL2C covariant correlation function. So that would be a 2D conformal correlation function. Okay, and I put this in quotes because actually there are a few subtleties, which were some of them were mentioned yesterday, but I guess for now, what is more important is the actual symmetry action on this. Okay, so if we were to take seriously this story, then there will be a 2D OPE, where I take my graviton, I'm just gonna call it G, at location Z1. Then I take it to be very close to another graviton, say at location Z2. So these have some weights, delta 1 and delta 2. And then the result happens to be the angular momentum operator to some weight n, and a pole at Z1 minus Z2. And then there's an extra state here that just becomes collinear with Z2 because I'm taking the OP. So this residue is applied to this part of the operator, and this operator sometimes we call it Rn, just because it's evaluated at delta equals moment. Okay, so that's the structure that I derive from this collinear limit when I take Z1 to be very close to one of these, say Z2. Okay, so it turns out that this here I can actually interpret as another graviton that has shifted weight. But to explain that, I need to be a bit more precise with what the operator is. With what J, the angular momentum generator, does. Okay, so this is what connects to the W algebra. Okay, usually we write this J as an angular momentum generator. Maybe a good formula to start with is something that looks like this. So in momentum space, the angular momentum actually acts on the momenta and on the polarization. So this assumes that I'm acting on an amplitude that has some gauge symmetry. And then what I mean by J here doesn't have mu and nu indices. So it's actually contracted with F1, which is the field strength of this graviton. So it's gonna look like this. It's gonna look like P1, epsilon 1, mu nu. So I take one of the polarization vectors of a graviton, and I antisymmetrize it with its moment. Okay, so this is gonna be maybe the starting point to explain what I want to explain. We're not gonna use this language because we don't like polarization vectors, and I think computations become a bit more cumbersome in polarization vectors. But this is a way in which we can actually introduce what this action is. But remember, yesterday I told you, no, what we need to do is, because we are looking at the celestial sphere, we need to introduce this angular, spinor helicity variables. Right? So the advantage between these spinor helicity variables and the momentum variable is that the helicity variable allows me to transform SL2C. So I have SL2C acting on lambda and lambda tilde. And then this angular momentum, which was an SL31 generator, now becomes an SL2C generator. And I can quickly explain what the angular momentum transformation is. It has something. It's just that. Okay, so I take this formula and then I replace it in terms of lambda and lambda tildes, and I get this formula, which is an SL2C. It's an SL2C generator. And for that, I have to tell you what epsilon alpha dot is. So epsilon alpha dot is epsilon mu, sigma mu alpha dot. And after some computation, you can check that it becomes a reference vector times lambda tilde. Okay, and then essentially there is a chiral conjugate of this, which is lambda tilde alpha dot. Okay. So bear with me for a second that this is actually what's gonna be important. This is the language that we are gonna use, but this is the textbook explanation of this. Okay, so now I take my field strength and then I dot it with J mu. So there will be a term that looks like P1 dp contracted. So let me just put, and this multiplies epsilon 1 times P. Okay, if I do that in this language, so if I take this F nu J nu, the result is going to be something that looks like lambda 1 alpha d lambda alpha. There are more terms here. There are more terms here. I'm not going to do the full calculation, but I just want to illustrate this fact. So this is now a translation. So this is actually what connects to these symplectomorphisms, because it's actually a volume preserving translation, symplectomorphism, where the volume is measured in the light plane. So actually, this is the part that's going to be interesting, because this light plane, which I mentioned before, is like PU and PW. That's exactly this lambda, PU and PW. Okay. So now I can actually finally write the explicit formula that I was sketching. Okay, so the explicit formula is I take Rn defined in that way, and I act. Let me act on a graviton that depends on lambda and lambda tilde. Then I get, so let's just call this 1 and this 2. Then I get a pulse of 1 minus 2. And I get lambda 1 contracted with lambda 2 to the power of n, acting on lambda 2. Okay, that's the simplest formula. So when we actually wrote this algebra for the first time, there was, before taking the residue, there was a beta function, and things become very cumbersome. But once you take the residue and you write this operator in a simple way, the formula simplifies dramatically to this, and this is actually what suggests a connection to twistor theory. So roughly speaking, the twistor variable is the Fourier transform of lambda. So this is actually in twistor theory just a vector mu alpha. That's sort of the twistor interpretation of this. Okay. Is there any question about the notation? Because this is sort of the main structure in this stuff. Or is it? is it clear?
What is R1 engine?
And then for this operator.
Yeah, I define it here. It's the residue. I just call it R2 to mean it's a residue. Yeah, I call G just normal graviton. So this is still in momentum space. And R is a residue of that. Which, I mean, if you were to go through a computation, the R is the residue of a G. G has a weight delta. If you take the residue of something that is a many transform in delta, what this extracts is a term in the Taylor series of the variable you are transforming. So if the G is a many transform in the energy, the residue at 1 minus n is the n power of the energy of G. So essentially, we are taking a term in the momentum space that looks like omega to the n, omega 1 to the n. And this is why the original paper was called the soft or generalized soft theorem. Okay, just because at the time I thought that we can define the soft theorems to higher orders in n, in omega, in the same sense that the leading one is 1 over omega. But anyway, the whole thing is just a change of basis. So you can think of it as a different parameterization of the energy. And then, yeah, the algebra is the same in momentum space or in the formula. Okay, so
R1 acts with lambda 1 and then differentiating lambda 2. So really on the right.
Yeah. Let me just for now, I'm going to actually write the series. So Rn is a term in the Taylor series. But if I resum, so maybe I should resum it. Omega n Rn, and then I sum up all the n's from 0 to infinity. Then I recover my original graviton. Remember that lambda depends on omega in this way. So that's lambda tilde. And well, this is actually not entirely correct because to get this formula, one has to do what's called a little group transformation, where actually lambda tilde becomes proportional to omega instead of square root of omega. If one does the square root in both, which is the symmetric choice, then there's an 1 over omega here. But this is the way that's more clear to write the algebra. So for one last time, I'm actually going to write what it looks like for these states in this particular basis. So, remember the lambda tilde, but this lambda is in this frame. So the algebra becomes Z1, Z2. So it's Z1 minus Z2. This is actually SL2 invariant. I'm just going to write real quick what lambda 1, alpha, lambda 2, beta, epsilon, alpha, beta is. So that's Z1 minus Z2. Okay, and usually we denote this as 1, 2, just because this is SL2 invariant, so it looks like a determinant. So we have a bracket notation for this. It's not an expectation value. So yes, I'm gonna write it like this. And then this structure now can be written in the form of lambda tilde 1 alpha dot, lambda tilde 2 beta dot. So lambda again lambda tilde is light on momenta, And if you actually work it out, well, first of all, it looks like this. Set 1 bar minus set 2 bar. But we actually have, again, a special notation for this. Very creatively, we write it as a square bracket. Okay, so that's what goes here. And then, once I resum all of these things, actually, I get, thanks to this factorial, I get an exponential that looks like this. Acting on J lambda 2, lambda 2. Okay, so that's the simplest ever way I know how to write all these complicated topics. I didn't even start from the original formula. We actually got some complicated mess first. But then I think a year later, maybe 2 years later, actually, I wrote this formula in 2209 00696. And the nice thing about this formula is that, well, it started as being a Lorentz transformation, but because of some nice properties of these spin-orblicity variables, it ended up looking like a translation. So actually, this is a state that we can now write to be situated at lambda 2, but lambda 2 tilde plus lambda 1 tilde. Okay. Okay, so maybe one last thing about this formula is that originally we expect lambda tilde to have set and set bar, so to be defined on the sphere. I mentioned yesterday that C was a coordinate of CP1. But this formula actually tells you, well, maybe that's wrong, because actually, you see lambda tilde here, because of, again, we're going into this chiral world, we're in the self-dual world. So maybe this is not the right way to think about it, because now lambda tilde is very special as compared to lambda. And in fact, what this amounts to is to resum, if you were to compute the conformal descendants in SL2C, this will resum all the L bar. This will resum all the L bar descendants, because it's essentially acting with L bar minus 1. So if you look at a conformal block, you can compute these conformal descendants for L or L bar. This thing actually ends up resuming all of the L bar descendants. So it tells you, okay, maybe the original idea, which was set and set bar to be conjugate, is not very good. That motivates the title of this paper, which is to think of lambda tilde as completely different to lambda. So this happens in particular when both of these are in RP1. So set bar also is in RP1. And in that case, lambda and lambda tilde are independent and real. Okay, so that goes by the name of, well, there are many names for that. In the spacetime, it looks like 2,2 spacetime. In the celestial sphere, it looks like a 1,1 Lorentzian torus, actually.
Sorry, what was the last word?
Lorentzian torus, yeah, sorry, yeah.
Torus.
Yeah.
So there's no possibility that there's some dual formula which involves shifting by lambda instead of lambda tilde.
Right. You will find this formula if you were to study anti-self-dual sector. And okay, that's trivial. The non-trivial part is to combine them two in an interacting way. And that has been an open problem, I would say, since Penrose proposed that self-dual theory was sort of the vacuum solution, the sort of the ground state will be self-dual graviton, and then there will be non-linear graviton perturbations of it, which amounts to find an interaction between self-dual, anti-self-dual states. Yeah, and that's not the problem I'm trying to solve today, because I think I motivated pretty well the fact that self-dual theories are important, and by itself they have a lot of structure.
Lorentzian torus, does that mean that time has a periodic direction?
Correct. Yeah, correct. So the way that the Lorentzian torus emerges is that there are two closed cycles in 2,2 because the light cone is now connected, so you can go around in time. And one of those cycles is the cycle of the torus. Sorry, the two cycles are the two cycles of the torus, and the other are non-compact directions. Again, this is the natural way in which we can formulate this problem. We know from just the self-dual gravity that this problem is nice in either 2,2 or 4,0. It's never nice in 3,1 because of this complex problem in the Hodge wall. So yeah, this is natural now that we're talking about this class helicity. I should remind you all the time that this G stands for graviton, but it's always a plus gravity. It's always a circular polarization of that gravity. Okay, so after you start thinking of it like that, then you think, okay, lambda tilde is essentially just a structure constant. So I'm gonna write this formula in a very suggestive way where lambda tilde is upstairs and lambda is sort of downstairs, or is just this index. So lambda, I remind you, is just one set. So I have this lambda tilde, and then I have a pole. And then why cannot I just write f lambda tilde 1, lambda tilde 2, lambda tilde 3, where G now depends on lambda tilde 3. Because after all, it has nothing to do with lambda. And I can tell you what f is. Well, f is nothing but the structure constant associated to this transformation. So to write it explicitly, and now I should not write this as f. Let's just call it h. And f is lambda 1, lambda 2, lambda 3. Is 1, 2 delta lambda 1 plus lambda 2 plus lambda 3. And you lower the index by essentially doing a CPT on this one. So it's f lambda 1, lambda 2 minus lambda 3.
What was the square bracket of 1, 2?
Oh my god, I just erased.
No, it's fixed up.
Okay. Yes. So yeah, I call the square bracket the lambda tilde bracket, and the angle bracket is the lambda bracket, but now they have nothing to do with each other because they are independent in this thing. Okay, so now you can just keep playing, and okay, I show you that this bracket is just the classical limit of a Moyal bracket. So this f, which by the way satisfies Jacobian identity and all the nice structures, obviously, this f can be mapped to a Moyal bracket, and to no surprise, that becomes the OPE you would get if you study self-dual gravity instead of gravity. Sorry, Moyal deformed gravity instead of gravity. So the OPE that you would get, this structure changes by the deformation quantization of the bracket. That's no surprise because this theory was always secretly written in terms of a Poisson bracket, even though the amplitude was computed in gravity. Once you set most of the gravitons to be plus, then self-dual gravity has something to say. it's not exactly clear how to, so there are many proposals how to incorporate these two minuses as a perturbation. But I would say it's not exactly clear. What is clear is that from the structure of this amplitude, we get the same relation as the self-dual gravity. Okay. How much time do I have? I think maybe you should.
10 minutes.
5
minutes.
Okay, I have a small, sorry, I'm not the chairman, but I have suddenly I had an idea. So if we could have just 10 more, and it's not I will not talk. I have a suggestion for the group. Maybe if we can take 10 minutes today, Joe, still? Sure. Good.
So I'm happy to wrap up in like 5
Very
minutes.
good.
Yeah, and you have up to 10 minutes.
Yeah, I think I'll make it quick because I definitely, I don't think I will make it to the point where we can talk about non-commutativity and all that. But maybe yes, I want to flash something in the form of a table, and then maybe I can explain part of it. But I'm just gonna write a table where I compare.
By the way, does anything you do somehow generalize to some kind of higher dimension?
No. No, and that's good because we actually want something that's very four-dimensional. Indeed, twistor theory, although people have tried to extend the Penrose transform, which is the starting observation of twistor theory, is more intrinsically four-dimensional than anything else. And you can go to Oxford and talk to everyone, and they will tell you, yeah, you can do it in any dimension, odd dimension, very easy, the embedded formalism. But the whole magic of these solutions happens very explicitly in four dimensions. And yeah, there is no exactly good reason for it, except that in four dimensions happens to have some special structures. In fact, most of this was found starting from infrared divergence amplitudes which live in four dimensions. Anyway, so let's just do a twistor exploration. Okay, which is a 5-minute exploration on what the twistor symmetry is. So this can go really wrong like this, right? So twistor space is defined by two coordinates, mu plus and mu minus. At this point, maybe you can relate that to the lambda tildes. These are the conjugates. Strictly speaking, these are the conjugates of lambda tilde. Okay, so you have to Fourier transform these variables. But at the end of the day, you can think of this interchangeably. The important point is that 1, 2 bracket, right? So I have lambda 1, lambda 2. Becomes in this language, it becomes a Poisson bracket, which, yeah, just one. This was a bit close. So, but there's a symplectic structure, and the Poisson bracket is just the starting point. Then you can quantize this structure and ask what happens if you have, an H bar. That sort of quantizes to some sort of a Moyal bracket, for instance. And then obviously this is the classical limit. And then you can consider operators that look like e to the lambda 1 mu 1 plus lambda 2 mu 2. Okay, so let's just call these operators g of lambdas. The relation between this g of lambda is given by this quantum group structure. So you have some q which is e to the h bar, and that's how you get this 1, 2 bracket, the square bracket. So I'm just describing here the simplest quantum group structure. It starts from some Heisenberg algebra. And you can see now it looks very similar to this other algebra, or this algebra, if I just take the leading order in Q, right? So leading order in H bar, what I get is something that looks like 1 plus 1, 2 times E lambda 1 plus lambda. Okay, so all this quantum group structure simplifies in this large H bar, small H bar limit, and it gives me exactly the same thing as that, except that I don't have a denominator. Okay, so to fix that, what we consider is the enveloping algebra of this Heisenberg algebra. So I don't have time to go through that, but essentially that turns this new class, which were non-commutative coordinates, into some primary states. And the Heisenberg algebra turns into this OPE where I have an H bar by 1 and then capsule 1 times the identity operator. Okay. Now my state G, now depends on lambda tilde and also depends on a coordinate set. But it's given exactly by the same formula, lambda mu, that depends on set, except that because now this is a primary operator, in particular is the beta operator of a beta gamma system, I have to normal order. Okay, and the OPE between these G states is very similar to the bosonic string. You can compute it exactly. It becomes Q. Okay, let me ask you the OPE, the actual singular term, in the interest of time. That's 1 over 7 and 2 square and so on. So the leading order term in the collinear expansion, sorry, not the leading order term, the leading order term in the H bar expansion actually completely matches the gravity OPE derived from the other scattering amplitude and so on. If we start from this model, so this beta gamma model is actually a symplectic boson, but more interestingly, there is a 2D linear, nonlinear sigma model that has this exact structure. So we currently believe that there is a holographic correspondence between this 2D nonlinear sigma model and the 4D MHV amplitudes, which are all plasticity amplitudes in here. Okay, I think I should end up.